Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Stepping aside as we jump into section 2.4, the Big Ideas Math Integrated Math 3 textbook on solving linear systems. Now, you probably haven't done any solving systems of equations since IM1, if you remember the substitution method and the elimination method, and if you don't, hopefully these things will ring a bell, but as you've gotten better in algebra over time, just naturally or through experience, through IM2, whatever, hopefully these things will click pretty fast. But we did systems of two equations and two variables, just solving for x and y or whatever we had in word problems. This one's going to contain three equations and three variables. It's not necessarily harder, so to speak, but it is more. You actually have to whittle a system of three down to a system of two and then solve for that afterwards. So we'll see how this thing goes. This is, I thought this chapter was going to be a lot more graphing because I saw the very first part of transformations, and then later we had transformations, I think, in the next section for quadratic functions, but not a lot of graphing really recently. I mean, we hit scatter plot things last time. I don't think this one has graphs. So, sorry if I tease so many graph things and this doesn't have any, and we'll see how this goes. But if you want to find out more about this stuff, and you want to find something specific to your needs, jump to the description section down below. You can download the actual PDF and scan through that and see what you're looking for. I'm going to start with the problem set, the lecture, and then I'm going to go to the problem set after. You can find the problem set in the timestamp down below, wherever I start problems 1 and 2, or numbers 3 through 43 is what we're going to do as a whole. So let's go ahead and get started. Enjoy the dark night in the background. All right, so we're going to learn how to visualize solutions of systems of linear equations in three variables. Interested to see what they do with that, because three variables would mean 3D graphs and planes. I'm sure you might not really know what that means or looks like, but we'll get ready for them. We'll probably look at what it means to be one solution versus no solutions, or infinitely many, though. We're going to solve systems of linear equations in three variables algebraically and solve real-life problems. So word problems presented where we might have to come up with a system of equations ourselves. Okay, so core vocabulary, linear equation in three variables. System of three linear equations, solution to system of three, ordered triple. Just all these three things just mean what they mean, right? They have to do systems of equations. Last one, ordered triple. Think about the phrase ordered pair. Ordered pair is an x comma y. Ordered triple is an x comma y comma z, right? That's what we're doing with those ones. Okay, previously you would have known what a system of two linear equations was. I don't know how often we've been diving into system of two, right, for previous problems, but it's something you would have done from at least IM1. So anyway, okay, so a linear equation in three variables x, y, and z is an equation of the form ax plus by plus cz equals d, where a, b, and c are not all 0. So basically, it's three equations, three variables, 3x plus 4y minus 8z equals negative 3. Not much to say about that as a whole. Just these are all different linear equations in three variables. Okay, but the basis behind this is I can't solve for any one variable in one single equation that has three variables in it, much less two. And I couldn't do it with only two equations as well, provided that there's, independence in the system. I would need at least three equations for there to be enough scatteredness to get the one single solution that there would be for this particular instance. Just like a single equation with two variables. You can't solve for either one and get an actual number because there's an infinite set of solutions for that case. Anyway, the following is an example of a system of three linear equations. So with this system, we want to try and solve for x, y, and z. The solution to the system is an ordered triple, x, y, z, whose coordinates make each equation true. Now, we're not doing 3D graphs. I shouldn't say we're not. I don't know if we are. I don't anticipate we're doing 3D graphs, and so you probably don't really know what that looks like. But just to remind you of a system of two equations, I'm not going to do an example, but when you have an example of a system of two equations, let's say it was this plus that equals that, whatever, and you solve for that x, y ordered pair, keep in mind what all that means. It means your two equations have an infinite set of solutions on their own, but together they cross through one ordered pair, and that one ordered pair is a solution to the system. So these ones have a 3D graphical representation where these equations make planes, and those planes all intersect, hopefully, potentially at a single point of intersection, even if they're planes. Actually, here's a plane down here. I didn't even look farther down beyond my picture. The graph of a linear equation in three variables is a plane, I should have just read on, in three-dimensional space. But I wanted to remind you what this looks like, by the way. The graphs of three equations, the graph The graphs of three such equations that form a system are three planes whose intersection determines the number of solutions of the system, as shown in the diagram below. So you can have exactly one solution if those three planes, and you can see there's like this kind of purplish plane and this blue one and this blue one, they're all intersecting together at a single point. All intersect together at a single point. Any two planes intersect to form a line, such as there are two of the planes that intersect to form this line right here. There are two planes that intersect to form this line right here, and two planes that intersect to form that line that would go through there. And then those three lines intersect and are concurrent at that single point, which is just, where's the third? Which is just another case that I'm making there, that's the single point of intersection among all those three. So we're not going to graph these, but that's the representation of a single solution. You can have infinitely many solutions if all the planes coincide in such a way that their points of intersection all lie in a single line, such as that. I guess they already drew it. The line is a single line such as that one, but it needs to be all three planes together. Now, what does the equation set look like algebraically? We'll take a look at it. When you have infinitely many solutions in these cases, it's when one line is right on top of the other, like that. So it doesn't mean all real numbers. It just means that whatever is the solution of one is the solution of the other ones, and there are infinitely many of them. And no solution is the case where even if there's an intersection of two sets of planes, like these ones intersect together here, these ones intersect together, these ones intersect together here, there's no point of concurrency or lines or whatever among all three sets of planes together. So this is no solution for all three equations in the system. This one, even though if it intersects with two places, doesn't intersect all together as one, and these don't intersect all together, they're all parallel. Those are no solution cases graphically. So I think that checks off that first bit right there, visualize solutions of systems. Even if you don't know how to make these graphs or what these graphs specifically mean, we know how intersections work. And the idea that all three need to intersect together at a certain point or set of points to be a solution to the system means this is why this would be a no solution case versus infinitely many versus one. What does it look like algebraically? We're obviously going to do examples. So, solving systems of equations algebraically. Now, I did mention methods. I mentioned the substitution method and the elimination method. We'll see which ones they land on or if they force us to do one or the other based on examples or the problem set. The algebraic methods used to solve systems of linear equations in two variables can be extended to solve a system of linear equations in three variables. So, solving a three-variable system. Step one. You want to rewrite the linear equations in three variables as a linear system in two variables by using the substitution or elimination method. Yeah, basically, you have x, y, and z, all three variables there in all three equations, maybe. You want to turn it into a system of two. Use elimination to get rid of the z's in two sets of equations and make it say x and y in two of them. So you're turning a 3 into a 2 as you solved a 2 before. And then you got to work backwards. So step 2, solve the new linear system. Step 3, substitute the values found in step 2 into one of the original equations and solve the remaining variable. So if you eliminated z, or use substitution method and got z by itself in a scenario, and you have only x and y left in your system of 2, solve for x and y, and then plug in that x and y into an original equation where z was maybe canceled, and you can solve for z ultimately, and you'll get your order triple. When you obtain a false equation such as 0 equals 1 in any of the steps, the system has no solution. This is a case where all your variables cancel and the left side doesn't equal the right side. That's true for a system of 2 as well. That's true for any set of equations. And when you do not obtain a false solution, but obtain an identity such as 0 equals 0, left side equals right side when all variables cancel, that's infinitely many solutions. So we saw what that visually looks like. Here's what it algebraically looks like. And you've seen that in the past if you remember anything about systems of equations. Maybe this is going to be the good refresher for you. So let's look at example number 1, solving a three-variable system that has one solution. Now, we don't know it has one solution beforehand. We do because they told us, but we won't know when I'm given that, I don't know if it has one solution or not. That being said, I wanted to bring something up. I forgot what it was. Oh, there are so many ways you can solve these guys. I'm just going to solve them in one particular way. The book's going to solve it in one particular way. There's an overabundance of like 30 something ways you can solve any one system. So if you just follow along with me, that's up to you. If you hear which way I'm going to go about it and you want to try it on your own, then great. If you want to try it on your own and see if you get the same answer as me, awesome. The way that I'm going to do it is just going to be my choice. It's not necessarily going to be best. It's not always going to be, I might even strategically not do it the best way sometimes and say, let's try it this way. So just be aware of that. You can make choices, and I want to see what choice they make here. I don't even know what method they're going to choose. They're going to rewrite the linear system in two variables. Looks like they're going to use elimination method and get rid of y. Now, if you notice what they did here was they took this bottom equation and they multiplied everything by 2. Now, why did they multiply everything by 2 in the bottom equation here? So that this negative y turns into a negative 2y. So that it becomes the additive inverse. It becomes the additive inverse of the positive 2y, so they together can cancel out and y is eliminated. We now have a new equation that says 16x plus 11z equals 6. It looks like their goal is to eliminate y's in 2 different sets of equations using what you have up above. And then they're going to have a system of 2 equations with just x and z. I'm wondering where my water bottle is. I might have to pause in a second and grab it. Anyway, so they did that to eliminate the y's, and they added down these lists. Now, if they ever subtract down the lists, and you'll see what I mean when I say that, but if they ever end up subtracting down the list, guys, I'm always going to add. So I want to make sure these are always opposite signs. 4x plus 12x is 16x, 3z plus 8z is 11z, 12 plus negative 6 is 6. Anyway, so they take now a different set of equations. Looks like they're going to do the bottom equation, and they're now going to multiply it by 3 times 3, and then, or negative 3 probably. Let me take a look. Yep, times negative 3, so that these signs change. 6x is negative 18x now. Negative y is positive 3y, because now it can cancel with this negative 3y there, and then you combine those. Now you have 2 different equations. Now, I don't know if they planned on this or if the problem was set up in such a pretty way for this to happen, but now you have 2 equations making a system of 2, where this one and this one can be used to now solve for x and z in that system as we would traditionally, whether you use elimination or substitution. But they used elimination to solve for y first by manipulating either a single equation or multiple equations, and that's where it's kind of a your choice thing. And I get where they made this choice. I can think of a way to eliminate x's if I wanted to. I could multiply this one by negative 2 and eliminate it with this guy here, or multiply by negative 3 and eliminate it with this guy here, if you know what I mean on that. They could have done that, and they didn't. That's where I'm saying you can do more than one way. Anyway, now to solve the system of 2, elimination is prime and set up for this. 16x minus 16x is 0, and this would now combine to be 4z. This combines becomes 8. You solve for that, you get z equals 2. Once you solve 2 for z, you can use that to find x by substituting it into either of these equations. I would definitely choose one of these two. I guess the top one. Choose that top equation there, substitute 2 for z, you get 16x plus 22 equals 6. Subtract 22, and you get negative 16. Divide by 16, you get negative 1 for x. So just do the algebra on that afterward and go back to it. I'm going to show more work when I do the problems myself. And now you have 2 and negative 1 for z and x, and you can use that to find y. So if you take an equation, one of the original ones, looks like they chose this equation here. They take the bottom equation, 6x minus y plus 4z equals negative 3. They're going to substitute negative 1 for x and 2 for z to solve for y in this situation. You know, do the algebra, you end up getting y equals 5 apparently. When you get all 3 of those, you need to write your final set as an ordered triple. It must be written as this negative 1, 5, 2 in parentheses ordered triple to indicate the point of intersection. That's the single solution of these 3 planes that would have been graphed together. Same way as, going back to this problem, same way as this xy being an ordered pair for the point of intersection for here, you always write your answer as an ordered pair. So this one should be written as an ordered triple. Don't forget that. The only time that we won't do ordered triples, well, if it's no solution or infinitely many solutions, but the only other case is with word problems. If they have actual context to these numbers and you're like, oh, this person owes $1 and this person gets $5 and whatever it is you're talking about, we might have to write that in context. Outside of that, for traditional problems like these, single solution, write the ordered triple. Okay, hopefully that's a good way of bringing things back into what it looks like. Let's now see what it looks like to have a no solution case for a system. So they're going elimination method again. They're taking this top equation, it looks like, and they're multiplying the whole top equation by negative 5 to, maybe their plan was to eliminate x's with this one, but if you'll notice here, as this one also gets brought down, you'll notice that everything actually eliminates. This is 0, this is 0, this is 0, and negative 10 plus 3 is negative 7. So you get an equation now that says 0 equals negative 7, all the variables are canceled, and that's a false statement. When that kind of thing appears, assuming your math is right, that's a case of no solution. That might mean that all 3 planes are parallel to each other, and they just never intersect with each other, and that's just a classic case of that. So if those pop up, better for us, it's less work. You can see there was quite a bit of work to do in the first one, even if it's by strategy and organization, or just by me talking about it. Anyway, that's a no solution case. Nothing more to write besides no solution. You do have to declare no solution there. There's an infinitely many solutions case as well. Let's take a look at what they want to do here. Looks like a straight elimination of z by taking these top two equations down will work out. Z minus z is 0. Those go away. You get 2x minus 2y is negative 6. And then you can also eliminate the z's with this second equation and the third equation. Negative z plus z there. And I would have done it the same way. Those eliminate as well. You combine these, you get 6x minus 6y is negative 18. So now we have these two equations here as a system of two. 2x minus 2y is negative 6, and 6x minus 6y is negative 18. They write them down below, but what do they do with the top equation is they multiply everything by negative 3 as a plan perhaps to eliminate the x's. 2x times negative 3 is negative 6x, and now these can eliminate here together. The problem, or not really problem, but the interesting part is negative 2y times negative 3 is positive 6y, which means these eliminate as well, and the 18s eliminate, which is really, or they become 0. Which is really no cause or concern for us. That can turn into 0 as many times as we want. But when the variables are gone and you get 0 equals 0, that's a case where you have infinitely many solutions. Infinitely many solutions when all variables are gone and yet the left side still equals the right side in a true statement. Excuse me. Describe the solutions of the system using an ordered triple. One way to do this, I didn't think about this. Hold on. One way to do this is to solve new equation 2 for y to obtain y equals x plus 3. I didn't see this before. So they take new equation 2, I think this one right here. They're taking this equation and they're rewriting it. Negative 6y equals negative 6x minus 18 divided by negative 6. They get y equals x plus 3. And then substitute x plus 3 for y in the original equation. Yeah, so I guess the purpose of doing this is to say infinitely many solutions is to also state what those solutions are. Substitute x plus 3 for y in the original equation 1 to obtain z equals 0. So if x is indeed x, and you can rewrite y in terms of x, and you can plug them back in to solve for z, let's see what that would do for you. They said take the original equation 1 to obtain z equals 0. Substitute. I want to see how this works. I didn't anticipate this portion. I thought you'd say infinitely many solutions and move on. So I have x minus, and then x plus 3, this is y, plus z equals negative 3. And I guess the idea behind this, guys, is the x's should ideally cancel. That's the whole thing about the infinite solution set. Now it becomes x minus 3 plus z equals negative 3. X minus x is gone. Negative 3 plus 3, add it over is 0, so z equals 0. So yeah, the new way to write that system for this infinitely many solutions, it may be infinitely many, but it's still dependent on one of the variables to write basically what that line will represent. Whatever x is, y will always be 3 greater than x, and z will always be 0 in that case of that line. That's what keeps its two-dimensionality going on. I guess it's on the z-axis, or the something axis, I don't know. Anyway, that's the solution to the system there. All right, good for me to check that out. We don't stop at infinitely many. Okay, solving real-life problems. Let's solve a multi-step problem here. An amphitheater charges $75 for each seat in section A, 75 per in each seat here, 55 for each seat in section B, and $30 for each lawn seat. There are 3 times as many seats in section B as section A. So here's the thing. We have to come up with equations for this. And I say equations, normally 3 of them. So when I'm already looking at, and they're already planning it out, when I'm looking at what I need to write, this first one already starts off with some form of, I can come up with an equation with this information and the amount that's made from there. There's something that says how many seats there are in total. That's the second equation. And a third equation is comparing section B to section A. I'm seeing that. So 3 times as many seats in section B as in section A, and the revenue from selling all 23,000 seats is 870,000. How many seats are in each section of the amphitheater? So here, what we want to do, and it looks like they're using X and Y and Z for these things. X is representing number of seats in section A. I probably would use A, B, and C personally. X is number of seats in section A, Y is number of seats in section B. If there are 3 times as many seats in B as there are A, B is 3 times, or excuse me, Y is 3 times X. So that's an equation for that second bit of information. That was in, I used black. So that was in black. So that's that guy there. The second one is the total quantity of seats, the number of seats in A, X, plus the number of seats in B, Y, plus the number of lawn seats available, Z, equals 23,000. That's ideally the green. They don't say anything like X plus Y plus Z equals. You're going to have to come up with that for yourself. That's the total amount. because that's number of seats plus seats plus seats equals seats. And the last one's a dollar amount, which is based off this stuff here. I'm not going to get deep into this. We should know how to write some equations with this form. But 75x means $75 per seat times the number of seats. This is money, the revenue or cost of all X number of seats when they're $75 each, plus the dollars made in section B, plus the dollars made in section C equals the total dollars made, 870,000. This is your system of 3. Now, when I'm looking at this problem, I'm seeing an opportunity to solve using a different method, such as substitution. Because y equals 3x, you can substitute 3x for y, and it looks like they're actually going to do that here as well. So 3x takes y's place here, and now you have an equation that says 4x plus z equals 23,000. That is a two-variable single equation. You can now substitute 3x into another equation, such as the bottom one, right? You can't re-express it in the same equation you have, but substitute it into this one as well and re-express that. So this is solving using substitution, at least initially. So you have 4x plus z equals 23,000 and 240x plus 30z equals 870,000. And then they take those ones down here to now solve, and you can go ahead and use elimination or substitution, all according to what you want to do here on out. They multiplied 4x plus z, it looks like, by negative 30. So they can eliminate the z's here, so times negative 30 for that one. And they use elimination to then solve the rest of the way. You get x equals 1,500. When you plug 1,500 back into an equation that has just z in it, such as probably this one, 4x plus z, you do smaller ones when you can, you get z equals 17,000. And when you plug in 1,500 and 17,000 into maybe this equation, you can use that to solve for y, and you get y equals 4,500. Seems to check out as well, right? 4,500 is 3 times as much as this, and you can double check everything. Now, the solution, as they wrote as an ordered triple, is this, but I would say it more as a word problem. I would leave it in context. So that's the ordered triple answer, but I would instead say what they say next. There are 1,500 seats in section A, 4,500 seats in section B, and 17,000 lawn seats. Okay, listen, before I move forward into this, now that the lecture's over, let me find my water bottle. I'll be right back. It was right by my bedside. Okay, let's start with the vocabulary and core concept check right here. Number 1, vocabulary. The solution of a system of 3 linear equations is expressed as an ordered triple. If it's a single solution, they said the solution. So an ordered triple. That is an x, y, z set like so. And I'm glad that they express that. They're telling you, do it. Do it. Don't leave that part out. Number 2, writing. Explain how you know when a linear system in 3 variables has infinitely many solutions. Well, now they don't actually say this exact phrasing that I'm going to say right here, and I tend to not like to say this phrasing otherwise, but when all variables cancel and the left side equals the right side. That's the layman's terms version of it, something that you guys would generally probably remember more, but it's, you end up having a statement, a true statement on left and right involving only constants. 0 equals 0, 2 equals 2, negative 7 equals negative 7, whatever it is where there are no more variables involved. It's not dependent on the variables anymore to make the solution true. It just is what it is no matter what. All right, guys, I'm going to go ahead and get started on the rest of the problem set here. Let me see how many we're going to do. We're going to 3 to 43. Numbers 3 to 43. If it's solving systems of 3, it might take a while, right? Especially if I want to talk strategy, talk shop, do different methods, things like that. So let's go ahead and get started here and see what they want us to do. In 3 through 8, solve using the elimination method. Okay, so they're enforcing elimination method on us, and if you saw the lecture portion of this, then you fully understand how that works. I got to write these out regardless of what I do, so I'm going to talk through what I'm writing out. What I do want to mention on this set is that even when the book solved using substitution on one of the examples, they did it on the system of 3 where they used substitution. They did not continue using substitution when they got it down to a system of 2. Now, so if they force us to use substitution later, I can go to elimination on the system of 3 later, I suppose. You don't have to stick to substitution the whole way. That being said, let's go ahead and solve using elimination now. And I'm going to organize my work best I can with color coding things. It's just going to take a while. And I'll just make choices. So my choice I'm going to make here is there's a great way to eliminate z's or to eliminate x's. I'm just going to eliminate x's because they're at the forefront right here. If I take the top 2 equations, let's just call them 1 and 2 right here. I'm going to rewrite 1 and 2 down here as x would ideally cancel out right now if I just add down these lists because the x's are additive inverses, right now. So when I add down these lists, x minus x is 0, that's gone. Y plus 2y is 3y. Negative 2z plus z is negative z, and you get 7. So I have a brand new equation right here, 3y minus z equals 7. I now plan on eliminating x in another set of equations, such as 2 and 3. Let's see, I'm not going to keep writing the 1, 2, stuff like that. But such as 2 and 3, equations 2 and 3, I can eliminate x there if I take the top, or this equation right here, and multiply it by 2. Because then, with the third equation, 2 and 3, I don't know if this is how I always want to lay it out, but maybe this will help you. Negative 2x plus 4y plus 2z equals 4. I multiplied everything here by 2. Don't forget to multiply this one by 2 as well. People tend to forget that. And then here, rewrite this the same way. 2x plus 3y minus z equals 9. Sorry if that looks a little small for you. I'll try and fit everything better next time. Maybe I can't write these ones each time the same way. But negative 2x plus 2x is 0, and that's my plan, to get rid of the x's and solve the rest of the way. 7y plus 1z equals 13. So now I have two brand new equations here and here where I can solve using whatever method of choice. Maybe I could use substitution here if I wanted to, but I think elimination is proper. In fact, the z's are lined up to eliminate right now by adding down these lists as we did before. 3y plus 7y is 10y, and here we get 20. Divide both sides by 10, you get y equals 2. Now, just a heads up, I don't know what the book's going to do for answers. I'm sure you can get an answer that's 1/2. But if you get an answer that's 13/24 or something like that, something might have gone wrong. And there's a chance I can screw up somewhere here. I don't anticipate doing so. But if I do, I'll either carry forward, or I might pause and say, let me make sure. And then I'll say, okay, I believe it, I'll carry forward, or whatever it is. But if I get fraction answers, I will be at pause. And I want you to think the same way. Normally, these things are going to help you be rather clean, unless it's some sort of challenge problem. Anyway, y equals 2. Now let's solve for z. Take one of these equations from before, like this one. Substitute 2 for y. You get 7 times, 2. I was going to put 14 right there. You get 7 times 2 plus z equals 13. That is 14. And here you get z equals negative 1. And now I can solve for x using one of the original equations now that I know that y is 2 and z is negative 1. So let's go to, I don't know, x plus y minus 2z equals 5. X plus y minus 2z equals 5. If there's one thing that, because I think I, for the most part, prefer elimination when it's already set up in standard form. X plus y, x plus y minus 2z equals 5. But substitution has its benefits if x equals 1. It has its benefits at the end because x would already be by itself in this case, and you can substitute on the other side. So my final solution will be an order triple. It would be 1, 2, negative 1. That's the final set once you do all the substitution on that stuff. Now, whether I substituted y, 2 for y, negative 1 for z in the top equation, middle equation, or bottom equation, I should have gotten 1 for x regardless. That's the point. It's the solution to the system no matter what you do. All right, that was just one question. Yeah, this might take a while. Number 4. Depends on how much I want to organize this stuff, because if I did it myself, it would be a lot sloppier work, but I'd still get it done, and I'd get it done in about 1/3 of the time. So I'm sometimes thinking, how sloppy do I want to go? But really, I got to ask myself, who's this for, me or you? I'll answer it easily by saying it's not for me. So I might have to organize it in some way that you can follow and say, wait, where did this come from? Why did you do that? One of the more frustrating things about watching a video is you can't get, a response back when you want to ask something. You're like, wait, how'd you do that? I missed that part. So hopefully everything I do, you can see and you can follow along with. Such as, I'm going to take equations 1 and 3 and do the same thing. I'm going to eliminate x. I'm going to look to eliminate alphabetically if it seems feasible to do so, and x looks just fine. Any of these are just fine to eliminate no matter what you do. But I'm going to eliminate x in this case because that's my choice. So in this one here, x is just as feasible as any of the other ones, so I'm going to do it. And right now, I don't have to change anything in these equations 1 and 3 to do so. That, is totally wrong. 2y minus 4z equals 5. Now, some of you guys might do things in your head, and I get that. I might rush on some of the ones later and do it in my head as well if you think that it's easy to notice what I'm doing. I might do them on systems of 2 within a problem, though, to start off. Anyway, the x's go away here, and you're left with 6y minus 10z equals 4. So there's one equation set with y and z. Now let's eliminate x's in another way. Let's take the bottom equation and multiply it by 2. So now we can eliminate it with the second equation. All right. So yeah, you need 2 bits of information for this thing to work. Didn't really give myself enough room again. 2x minus y plus 2z equals negative 7. I really got to learn. And then negative 2x, that's where those will cancel, plus 4y minus 8z equals 10. That's the multiplying by 2 effect. As these are gone, we now have 3y minus 6z equals 3. So now I have a system of 2 in place with this guy and this guy. Let's see what they look like together and see what you want to do to solve here. And this is where you can get really clever, excuse me, with what you do. I'd rather eliminate y than eliminate z because it takes just multiplying by 1 set to eliminate y here, whereas here might take 2 things to eliminate z. But you might say multiply by negative 2, and there's nothing wrong with that. But check this out. You can also do this. You could take the top equation, and you could say divide by negative 2. Why make things bigger when you could make things smaller? I can make this negative 3y like that. And then plus 5z equals negative 2. You'd have to be careful on when you can divide and when you can't, really. It's just the idea of do things stay integers or not, and that's really what I aim for. Can I keep things small and keep things as integers is always my question. So when I eliminate here, I get negative z equals 1, so therefore z equals negative 1 would be one of my solutions there. Now I use that to solve for y. Let's just go ahead and take that into this equation I originally had here. 3y minus 6 times, negative 1 equals 3. Pardon my speed on a situation like this. I'm just going after it. So y also equals negative 1. We got z and y equaling negative 1. We can now solve for x in any of the situations here. Maybe I can take equation 1 and do exactly that. So in that top equation, x plus 4y minus 6z equals negative 1. Let's do more of a quick substitution. These are both negative 1, so 4 times negative 1 is negative 4. Negative 6 times negative 1 is plus 6. Like that. So x minus 4 plus 6 is x plus 2. And x, I was hoping would be negative 1, but it looks to be negative 3. So my order triple on this problem, only 2 problems fit on a whole, or took up a whole sheet of paper. I don't know if your binder paper acts the same way if you write just as big, but I'm getting negative 3, negative 1 as my order triple. And hopefully you got the same thing. Hopefully everything lined up. Okay, let's go on to, oops, something just popped up. Give me 1 second. Okay, let's go on to number 5. 2x plus y minus z equals 9. Let's try and eliminate another variable. I think z looks best this time. 2x plus y minus z equals 9. The less work, the better, basically. Negative x plus 6y plus 2z equals negative 17. And 5x plus 7y plus z equals bao. Bao pashao shishao. All right, my plan to eliminate z comes more in the form of I don't have to manipulate either equations 1 or 3 to make this thing actually work out the way I want it to. I can just add down those lists and I'll be good. Maybe this is one that we can do together and, with speed. See if this makes sense to you. I'm not doing this as multiplication. I'm just writing this in green. Let's eliminate right now. You see the negative z and the z? Let's cancel those out. Boom, those are gone. 2x plus 5x is 7x. This is for 1 and 3. 2x plus 5x is 7x. Y plus 7y is 8y. Negative z plus z is 0. 9 plus 4 is 13. So that saved me some time in doing that, right? That was a little faster in working that out that way. And I hope that you agreed with it and that you could understand what I did with it too. Now I need to eliminate z's in another set of equations. I can't do 1 and 3 again. Let's use maybe 1 and 2. Now, why am I choosing 1 and 2 instead of 2 and 3? Because 1 already has a negative z, right? This is positive. I'd have to multiply this by a negative to change it, and that leads to more possible mess ups. So here, if I multiply this whole thing by 2, I'll just write it up above. I got 4x plus 2y minus 2z equals 18. Now let's eliminate z's here. Take a look at this equation and this equation. See if you can make sense of this. This is a modified 1 and 2. So modified 1 and 2, we now will do 4x minus x, which is 3x. 2y plus 6y is 8y. Negative 2z plus 2z is 0. And 18 minus 17 is 1. So that's the makeshift redo of this one. And look at how much room and stuff I saved by doing that. Was that not enough writing for you guys to follow along with? Do you prefer the other way for me to do with you, for you to do with yourself? That's up to you to decide. That's where I'm going to I'm going to make choices. I'm going to make executive decisions on a per problem basis when I feel I'm going to want to do one versus the other. Now, right here is the same kind of thing, right? This 8y, if I turn it into a negative 8y by multiplying everything here by negative 1, negative 3x minus 8y equals negative 1. Now I can eliminate y and solve for x. Now, if I didn't write this, and I'm going to bring it back, but if I didn't write that, I could also subtract down these lists. I caution against that. I really do, because what people are going to do is eliminate this and then start adding these and forget when you're doing subtraction versus addition. That's why, and trust me, I say that all the time. I say it to my students, and yet they still do it anyway, and they make mistakes. So understand that when or IM1 students, maybe IM3 is a different story, and maybe your teacher will enforce it. But if you change the sign and act on it for what it is, I can now add down my list, and adding a negative becomes subtraction on its own. Anyway, so 7x minus 3x is 4x. That eliminates. 13 minus 1 is 12. And you get x equals 3. So now that I got x equals 3, we're now going to substitute that into an equation. Let's take this one up here. You get 21 plus 8y equals 13. 8y is negative 8, so y is negative 1. That should be negative 1. Negative 1. And now I need to solve for z. Let's use that bottom equation, number 3 of z, and substitute those in. X is 3, so 5 times 3 is 15. 7 times negative 1 is negative 7. And that's 8. So z is going to be negative 4. So you have 3, negative 1, negative 4 as your final solution set, your ordered triple. So, that's an instance of me writing less. I know I spoke a lot still, but writing less and maybe saves me time. At least it saves me paper space. I have a lot more lines to do. So you can see that a problem can be a lot cleaner depending on how much you want to do in your head. Or, just do without needing to rewrite certain things. I almost feel like, because I'm copying down the problems each time, I almost feel like copying and pasting the problem on there, but I don't think I will. If you have to do it, then I'm going to do it as well. I do it on graphs because otherwise it would take a long time, and I'd need to make sure that all the scales are good. But yeah, this is fine to do. And their graphs will always be better than mine because it's made on a computer. Okay, which one should we do here? I'll go for eliminating x's. It just seems right. If you're fine with me doing, because these are already in a row right now, there's nothing to change. So let's take 1 and 2 right now and do that same thing that we were doing before. 3x minus 3x is 0. 2y plus 4y is 6y. Negative z plus 5z is 4z. And 8 minus 14 is negative 6. So there's one equation. Let's do the bottom two equations now as well. If we multiply this one by 3, I'll go ahead and rewrite it. But I might be able to rewrite it right here if that's okay. 3x minus 9y, that's a 9, plus 12z equals negative 42. Now let's take equations 2 and 3. 2 and 3, do the same thing in eliminating x. 0, 4y minus 9y is negative 5y, 5z plus 12z is 17z. Sorry, that's a 7. And negative 14 minus 42 is negative 56. Okay, we've eliminated x's. Now let's eliminate another variable here. This one is not so easy to determine which one you'd like to eliminate. Was that a 17? No, that was a negative. What was this? A negative. Hold on, I might have had the wrong number. What was I combining? Oh, z's. I'm sorry, 5z plus 12z. Huh. Hold on a second. All right. Anyway, what was I saying? Oh, yeah. So in this case here, it's not as easy to determine which one you maybe want to get by itself or eliminate in a certain way because there's no one easy way to just go about it immediately. So what I'm going to do right here, I'll probably eliminate y's. It'll leave me with smaller amounts of numbers. I'm intimidated by, say, multiplying this whole thing by 17. But, one thing I also can do, I just mentioned in the previous problem, let's divide everything by 2 perhaps. If it makes things smaller to work off of, then that might be more helpful for us. If I divide everything by 2 here, this becomes 3y plus 2z equals negative 3. And now when it comes to eliminating y's, instead of getting a least common multiple with these numbers of 30, we can get a least common multiple of these numbers of 15, right? So now we can say take this equation here and multiply everything by 3, get negative 15y plus 51z equals negative 168, and multiply, I'm concerned whether I'm doing this correctly, and I multiply everything here by 5, and then down there I'm going to get, let's see, that one's there. This is where organization woes kind of come into play. Draw arrows, use colors, things like that. But now I have 15y plus 10z equals negative 15. I'm only going to trust I did this right if I have an integer answer. If not, I'm going to have to look back at things and go, oh, what happened? Oh my gosh. So 61z equals negative 183 divided by 61. You do get negative 3. I'm feeling good about things there. Now, was this the best way to do the problem? I don't know. I didn't have foresight in knowing that this would come up with numbers like this, but maybe no matter what, it would have. So I chose to eliminate x's through ease of eliminating x's. Great. I could have maybe eliminated z's. I could have multiplied this top equation by 5 and eliminated there, multiplied by 4, eliminated there. Maybe the x's and y's would have cleaned up so much better without that. I have no idea. I literally don't know. I haven't tried the problem that way. But this lent to some stuff that was a little big, right? And you do what you do. Anyway, I'm not done. I got negative 3 for z. Let's now solve for y. I made this equation smaller. Maybe I can do it with this one. So 3y, 2 times negative 3 is negative 6. So negative 6 equals negative 3. Add 6 over and divide by 3. You get y equals 1. And now we solve for x. Take an equation up here. Maybe this one right here. X minus 3y plus 4z. I'll just write it right here while I can see it. X minus 3y is minus 3, plus 4z is minus 12, in that case, equals negative 14, and let's proceed. And we get x equals 1. So my final ordered triple here is 1, 1, negative 3. Once again, I think I'm anticipating getting integer answers and potentially smaller numbers here. If things become fractions, they become fractions. I'm just going to leave them as they are, though. All right, that is number 6. Let's move forward. Number 7. 2x plus 2y plus 5z equals negative 1. 2x. So all these have 2x's here. I feel like eliminating the x's by multiplying one of these by negative 1 will be the best or quickest course of action up front. And yeah, we've gone by eliminating x's before. Why not? Now, I like to lay these things out with same spacing like this. I'm doing it a lot better than I was before because I'm consciously aware that I wanted to state that. If you space things out better like this, you know what you want to line up a little bit as well. 3z equals 14. Okay. Despite the fact that I wrote this how I did, I'm going to take one of these equations and I'm going to make everything negative on it, or I'm going to multiply by negative 1 on it. Which one? The middle one. Let's multiply the middle one by negative 1. And then if you do, here, let's just do this. If I multiply everything by there by negative 1, this becomes negative, positive, negative, negative, right? I didn't change the original equation because I wrote this in blue, even though you can't really see it well. Anyway, I'm going to merge equations 1 and 2 and equations 2 and 3, right? Because now they're in line together. I think that'll work itself out pretty well. So equations 1 and 2 will combine to become eliminated. This becomes 3y minus or plus 4z equals negative 3. And then equations 2 and 3, these eliminate. You get 5y minus 4z equals 12. So when you combine things here, look, these eliminate cleanly as well. That's nice. So you get 8y equals, 9. So you get y equals 9/8. I mean, I didn't do anything wrong numbers-wise, so I'm going to trust that that's the right answer. If fractions are what they are, we're good. Let's make sure I wrote the problem right. 2x plus 2y plus 5z is negative 1. 2x minus y plus z is 2. And I change these to negative. Negative plus minus minus. And then 2x plus 4y minus 3z is 14. Yep, that's good. Made it negative combined. 3y, 4z, negative 3. 5y, negative 4z, 12. 9, 8, eliminate, 9/8. Yep. Listen, that's the answer. I'm trusting, unless they made a goof on the problem, that's the answer. So that is y's value. Now, it's not, there's as much a problem in saying, did I do something right, as much as there is, now I got to use this answer moving forward. Now, 9/8 is an exact value, if you're curious. It is 1.125. Whoops. But I intend on using fractions the rest of the way, especially if some of them will become 1/3. I'm not going to round 0.3 or something like that. So I'm going to use fractions. This is where things get a little clunky, and we'll see how much room I actually now have to do this. So let's see. Let's take that and shrink it some. Hope that's okay, because I need the room. Okay, so 9/8 is an answer there for y. Let's now substitute it into one of these equations and solve for z. You're going to have fractions no matter what you do. So here we go. 3 times 9/8 plus 4z equals -3. We get 27/8. If you want to deal with fractions less, despite the fact the answer will still probably be a fraction, I anticipate all these will be fractions. If you want to deal with fractions less, do this to your equation right now. Multiply everything by 8, because that'll make that 8 go away. Now you have 27 here. Thing is, though, everything becomes 8 times bigger. That's just the cost. So this becomes 32z, and this becomes, now that's a 7, by the way. Some of my 7s are turning into z's, and that's -24. It's disease. Subtract 27. Is this going to be a, nope, -51, and z is -51 over 32, a fraction which I do not believe can reduce in any which way. That just is what it is. So now I got to solve for x by plugging these into one of these equations up here. Which one is x best off with? I don't know. Can any of these reduce the z's? How about where y and z are as small as possible? Remember what the original equation was? So 2x, positive 2x, minus y, 9/8, plus z, so minus 51 over 32. Minus 51 over 32 equals a positive 2. That was the original equation. Once again, if you don't want to deal with fractions and common denominators, get rid of them right now by multiplying by the least common multiple. It'd be the same thing as having a common denominator, but you don't have to write fractions as much. If I multiply everything by 32, 32 divides by 8 and 32, so that works out. So 32 times 2, 64. 32 divided by 8 is 4, times 9 is 36, so -36. 32 by 32 is 1, you're left with -51, and that equals 2. So now it's a conventional way of solving, even if the answer is a fraction. So -87 equals 2. Add 87 over, you get 64x equals 89, and x equals 89 over 64. I don't think, though, I think 89 may in fact be a prime number. So there you have it, and that is the solution set. So 89 over 64, 9/8, and -51 over 32. I don't think I did anything wrong. So, and leave them as fractions if you can. Like I said, I dealt with fractions pretty easily by busting my fractions. There it was. Now, my concern is if number 7 was a fraction answer, my concern is number 8 is also going to be a fraction answer. So I'm expecting it. We'll see what happens. Let's move to number 8. Now, doing it as a homework assignment and following along with me, maybe you're in better trusting hands with that. If you want to try number 8 on your own before you watch this, go ahead and try it. I can't guarantee it is a fraction or not. If it was on a test, that's probably one of those things where you got to raise your hand and ask your teacher, I got this thing, should I get fraction answers? There's sometimes we'll say that to students. They'll say, I mean, you can get fraction answers or not. Do you trust your own math? And I just walk away. I'm kind of mean. Otherwise, I'll assure them sometimes, no, these should be good numbers. If it's a fraction, it's going to be 1/2 or something. You'll be good. You'll get it at the end. It'll clean up. It'll clean up, man. But this wasn't very clean, yo. That is not very clean. That is dirty. It's a dirty answer. And I expect one here on number 8 now that I just saw that in 7. That being said, let's still play elimination the best way we can. I see eliminating y's very easily right here on equations 1 and 2. I'm going to start with that straight up. 1 and 2 by adding 3x and 7x, eliminating y's, and -3z plus 5z is 2z, and here you get -16. Before I even move forward, I'm almost thinking about dividing everything here by 2 right now. If I divide everything by 2, then I'll get 5x plus z equals negative 8. Normally, I wait to do something like that in case something else is already going to line up for itself, but I'm letting you know beforehand that that's something I see in my head really early on, and I say, hey, everything's 2 times bigger than it needs to be, unless that would have helped it, in which case I'll undo that and erase it if I don't want it. Now let's do, the reason I wanted to do y's is because these y's can clean up pretty well as well. If I take the second equation and multiply by 2. So let's take this equation and do times 2, and here we'll have 14x minus 4y, see how those line up, plus 10z equals negative 28. So those ones are equations 2 and 3, a modified 2 and 3. And we'll get 16x plus 11z equals negative 22. See, from the onset, dividing by that 2 really helps me, because now when it comes to me solving for z, I think I'm well set up to do so by taking this top, when I say top equation, this one right here, I take this equation and I multiply it by negative 11. That's where I'm going to eliminate z's down here. So I get negative 55x minus 11z equals 88. Now the z's eliminate, and you have negative 39x equals 66. Yeah, and x is, you know what, this reduces though. 66 over negative 39, that reduces, divided at least by 3, is negative 22 over 13. So that's an answer for x that I'm getting there, and so hopefully that one kind of pans out correctly, but that's a reduced fraction. It's also not one I can write as a decimal very cleanly, so I'm going to leave it as it is, but that was a fraction that did reduce. Anyway, yeah, dividing that by 2 I think helped me, because otherwise 2 and 11 has a GCF or LCM of 22 instead of 11, so I think that works better for me. All right, so I solved for x. Let's now solve for z, given what we have here. Take one of these equations, any one of them, and solve for it. I'm going to take the one with the smallest numbers, which is this one, 5x plus z equals negative 8. Once again, a good reason that I have that. 5x plus z equals negative 8. Now this is negative 110 over 13. Once again, as I've shown before, if you want to get rid of your fractions, you can multiply your both sides by, say, 13 in this case, which will at least eliminate the one down there. Negative 110 plus 13z. You're going to have to divide by 13 again in the end, though, right? I hope you understand that. I'm opting to not do common denominator at the expense of having to do the division again, ultimately. So I hope you're understanding that it's a pleasantry. It's a visual aesthetic to move forward in the problem just to get back to a fraction later. Is that negative 104, I believe? So 13z equals, at 110, 6. Z is 6/13. Now that I have, these are both 13ths, negative 22/13 and 6/13. Let's use those to solve for y. I think I have to copy and paste an equation that's up here. Which y is best? None. Let's just take the top one. Whoops, I think I missed the y. There we go. All right, so this top equation, we're going to replace, because I can't see. Oh, I guess it's over on this side, 3x plus 2y. I forgot I have the page right there. All right, let's substitute 3x. The cool thing is they both divide by 13, so when I eliminate fractions by multiplying everything by 13, I'll be squared away. So now I have negative 66 over 13 plus 2y minus 18 over 13 equals negative 2. I have a couple things I can do here. I don't just have to multiply by 13. I can also divide by 2. Is that too much for you to see? Like, I'm going to multiply everything by 13, but I can also divide everything by 2. I don't know. I'm not going to do the divide by 2 with you. It's something I would do. It's not something you're probably a fan of. Anyway, 13's cancel here. Negative 66 plus, this is now 26y minus 18 equals negative 26. Is the y going to be a clean value? Oh, never mind. These are still here. I thought these canceled. So 26y minus 84 equals negative 26. 68? No, 58. This can reduce as well. 58 over 26 equals, divided by 2, 29 over 13. 29 over, so all of these are divided by they're divisible by 13. How lovely. Negative 22 thirteenths, negative 22 thirteenths, 29 thirteenths, and 6 thirteenths. All right, that was, I don't know if it was arguably better or worse than the previous problem, but since I anticipated it being a fraction, and since they all divided by 13, some of the things ended up a little bit cleaner for me. So there you have it. That's number 8. And we're 54 minutes in to this thing. We have another many problems to still do, and I'm only 8 problems in. 6 problems if you really just count those. All right, error analysis. Numbers 9 and 10. In exercises 9 and 10, describe and correct the error in the first step of solving the system of linear equations. I hope I don't have to continue on the solving, but let's see what they have here. They took, I don't know yet. They took this equation and wrote it here. Then they took this equation. All they did was they turned negative x into negative 4x. They didn't multiply anything else by 4, which is a classic thing that people can do, just changing one thing and not change anything else. And say, yeah, that's fine. It's totally not fine, guys. It's totally not fine. They took the second equation, and attempted to multiply by 4 to eliminate the x's, but only the x got multiplied. Only the x term got multiplied by 4. And none of the other terms did. Now, it's not very common. See, the thing that I stated before is sometimes you might subtract one thing and add the rest. Okay, I get that. Normally, if you multiply something by 4 like this here, you will generally, so let's see, 4x minus y plus 2z. And I'm only going to do this one step here. So I'm just writing this one and this one. Anyway, most people would know to multiply everything by 4 on one side, but people sometimes forget to do it on the other side. So if you do times 4 here, they'll remember negative 4x plus 8y plus 4z, and somehow they just write 11. Nope, it's 44, right? You have to remember that that thing gets multiplied as well. So that's the one that people tend to forget. Anyway, when those eliminate, when you add down these and these eliminate, now you get 7y plus 6z equals 26. And I'm not going to continue on the problem, but that's where we get to on that stage in correcting the first step. All right, let's go to number 10 and see what they do on this one. It's the same system, it looks like. So maybe that's a good reason why we're not going to solve. They're using the same system. So on number 10, they take looks like the top equation and multiply it by 3. Oh, except, what's the mistake? I don't know if you see it. And they take the bottom equation as is. So what's the mistake in the top equation? This is the common one that they would do. They multiply the top equation by 3. But, I just said it, but they did not multiply the right side by 3. This is a classic mistake. Now that's my own comment. Don't write that. That's my own comment. I'm telling you guys not to do it. Be very aware. I hope I don't make that mistake. I tend not to. I tend to warn kiddos about it all the time. So, listen, let's do what they just did. I'm just going to rewrite that one part. 12x minus 3y plus 6z. All that's good. Top equation got multiplied by 3 on the left side. On the right side, negative 18 times 3. We need that. Boom, right there. Then they took the bottom equation, 3x plus 3y minus 4z equals 44. So all was good except that side. Now, did they add correctly here? 12x plus 3x is 15x. Yup. Those cancel. 60 minus 4z is 2z. Yup. And before, when they added it was correct, but it was the wrong numbers. This is negative 10. Okay, that's the correction to the mistake, and it looks like we're not solving the rest of the way. But they did... Listen, if their goal was to take those two sets and do elimination to get these equations by themselves, that's not what their purpose would have been, because they didn't get the same two variables by themselves. So I'm not going to solve this anyway, because I don't have like x and z together on these ones. I have y and z. So, okay, I'll keep moving forward. 11 through 16, solve using the elimination method. So probably no change there. The one difference is, and I don't know if I like this so much, because they're blocking this section. They do say see examples 2 and 3. Now, we did the lecture together before. My guess is this will say see example 1. Yup. And if you guys remember, example 1 was a one solution case. Examples 2 and 3 were either infinitely many solutions or no solutions. So what I don't like about this personally, although the problems will be quicker, what I don't like about this personally is that we know that's what the answers will be. If we get one solution, if we get fraction, whatever, something went wrong, I already know what kinds of answers to get here. So it's not spontaneous, like any problem could be no solution. No, these problems will be, or they'll be infinitely many. And the infinitely many will have a little bit more work to do. So we'll see what to do when those problems come up. Anyway, that's what this section's all about, it looks like. I don't know that as a fact, but since it says see examples 2 and 3, I believe that's what examples 2 and 3 were. And that's why I was like, why are we doing elimination again if it's the same setup? Oh, it's not. These are those. So, oh well. Listen, the reason I bring that up is because when it comes to your own quizzes and tests, I mean, they can show up whenever, right? All right, what do you want to eliminate? I'm looking at u, y's. Now, if I take y's, see, here's what I want to do. Let's take the middle equation and divide by -2. All these are even. If I do that once, I only have one equation to do that with, and then I can do the top equation with it and the bottom equation with it, and I can eliminate. So I get -3x plus y minus 2z equals 4. So with that in mind, I can now align equations 2 and 3, this being the old 2, right, or the new 2 and 3 right here, 2x minus 3x, y, negative y plus y, and then 3z minus 2z, and 10 plus 4. And now I can also combine equations 1 and 2. 1 and 2. I'm really laying this out differently from the first problems I did. The x's eliminate here as well. 3x minus 3x is 0, negative y plus y is 0, 2z minus 2z is 0, and 4 plus 4 is 8. You get 0 equals 8. Well, and you're like, well, Mr. Robinson, what about these ones here? I suppose as long as two equations have no solution together, that means they are parallel. I believe that's what it means, that they're parallel planes. Even if they intersect with the third equation somewhere, they don't all intersect together somewhere. If at any time you run across a situation where all the variables cancel, it doesn't matter what this is. If at any time you run across a situation where all the variables cancel and left side doesn't equal the right side, that leads you to a no solution case. It only needs to happen once, because if it happens between two sets of equations of three variables, that means those planes never intersect. So how can all three planes intersect together if two of them don't intersect together? They can't. So number 11, I'm done. I'm done on number 11. All right, number 12. But that's what I'm saying, right? You're going to have cancellation somewhere. We're going to see where it is eventually. Yeah, somewhere they'll show up. So number 12 equals. Okay, this one's interesting. I don't know if you can see what's going on in the bottom equation. In the bottom equation, what's going on here? There's no z term. So that's already a good sign for you as listen, not having a z doesn't guarantee no solution or infinitely many solutions. But what it does do is it helps you alleviate and say, okay, if I want to solve a system, I'll solve a system of two using this one and another one. So my basic goal for right now is to just take the top two equations and eliminate z. And they're set up to eliminate z right now. So if I eliminate z using equations 1 and 2, right now 5x plus 6x, or 5x plus x is 6x, y plus y is 2y, and z minus z, or whatever, is 0. 6 plus 2 is 8. Now I have these two equations right here, and I want to solve this system. I'm seeing something out of them right now. You'll determine it with me in a second. You know, I'm big on shouting out division when I can. Sure, I could multiply the bottom equation by -2, but I could divide the top equation by -2 as well. And if I do that, I'm going to have -6x minus 2y equals -5. And what you'll notice here is x's cancel, y's cancel, you get 0, and 8 minus 5 is 3. So I get 0 equals 3, another classic no solution case. Variables cancel, left side doesn't equal right side. I get the no solution. I get the no solution. Anyway, we move forward now. Let's go to next page, number 13. So on number 13, we get we have x plus 3y minus z. Yeah, so that's the thing, right? You do want to make sure your math is right along the way and say, did I do everything correctly? I'm not going back to double check. I know I'm expecting those in this problem set, so I think it looks pretty good. Now, if we just had a couple no solution ones, I'm sure we got to get infinitely many solutions here in a second, maybe on this problem. I don't know yet. But, ooh, I see something right now I'm going to already play with. But, oh, that doesn't eliminate everything. Never mind. What was I just saying? Oh, when you have infinitely many solutions, there's more to talk about on the problems, though, so be prepared when it shows up. Okay, I thought I was going to be able to multiply everything here. I'm still going to do it. I'm going to multiply this whole middle equation by -3. I was thinking it was going to eliminate everything. It looks like it will eliminate 2 of the 3 variables, though, and I'll see what I want to do with that after it. At least it'll solve for y. Solve for y. -3x minus 3y plus 3z equals 0. Now I'm going to merge these two equations together right here. And through elimination, see, this isn't the best organization of work. If you have your pencil and stuff, I would probably rewrite equations as often as possible. But here I get -y, as these cancel. -y equals -1, therefore y equals 1. And when you see that y equals 1, now you're starting to think, hey, this is a system, we can work off. Not so fast. We don't know how x and z work together just yet. So let's start substituting 1 into other equations and solve for x and z. You saw that these two worked dependently with each other. I don't know if that's worth diving into more. Let's see how the top equation, the reason I bring that up is because they'll just cancel out again together. So let's use another set of equations and see how they work together. Like, let's plug 1 in for y in maybe these two equations and see how that works out. Oh, those x's and z's cancel out together too. I guess it's dependent no matter how it works. The question is, what do I do with that again? If I solve, I got to think about that. If I solve for, let me plug in y. Let me take the top equation because we already solved for y. This is an infinitely many solutions case. I'll show you by doing just a little bit more here. I'm going to plug in 1 for y there. I'll plug in 1 for y in the second equation. X plus 1 minus z equals 0. Now, what you're going to get here, let's just rewrite them. 3 times 1 is 3. Subtract 3 over, you get x minus z equals -1. And here you subtract 1, you get x minus z equals -1. So there's not much you can do there. But that's the whole goal, right? Listen, everything here will cancel. You get 0 equals 0, right? So there's infinitely many solutions. That's the idea. Everything will cancel there. But we're not done. The idea here that I kind of saw in the previous thing is you have to now express one variable in terms of another and kind of say what line this whole thing travels along. Now, y equals 1 is a part of that system. But now you have to clearly define one of your variables as something and re-express your other variable in terms of that. So maybe we take one of these equations, the x minus z equals -1. Solve for one of your variables, like solve for x, add z over, you get x equals z minus 1. X in terms of z is z minus 1. Z can be represented as z. If z is z, then x is z minus 1. Whatever z is, x is z minus 1. And then y is 1, regardless of that. So there is a triple. See, infinitely many solutions doesn't mean all real numbers. There's a specific set for which they'll be. So x will be z minus 1. Y will always be 1, and z will always be z. That being said, what are some solutions on this thing? If z was 2, this would be 1, 1, 2. If z was 5, it would be 4, 1, 5. If z was 20, it would be 19, 1, and 20. That's the point. Those are the ordered pairs that fit on this thing, and you want them as far as like how you write it. I was trying to think what to do with y equals 1 and when they canceled, but I think that's what I do there. Okay. So that's one infinitely many solutions case. Let's go to number 14. If you didn't understand that one, let's find another infinitely many solutions one. Do it again. We'll do it till it makes sense to you. Hopefully it does. X plus 2y minus z equals 3. There's one thing I wanted to bring up, and I just don't want to write an example for it, but it's the Mr. Robinson, how come, I recall this, okay, when we solved systems of 2 equations back in the day, and we got infinitely many solutions, why didn't we write an ordered pair equation thing like that before? Because your equations were the ordered pair things. Your equations were already 2 variables. So the line was the number of solutions. y equals 3x minus 7. Well, that's x comma 3x minus 7. You don't need to write it in that case because there's no third variable for which you need a value. Anyway, let's keep going with this one. I see z's as easy elimination here if I eliminate using 1 and 2 and 2 and 3. So if let's use a single color here. 1 and 2, add down the list, you get negative x plus y equals 2. In equations 2 and 3, we get 4x here. Negative y minus 3y is negative 4y. Z's cancel, and you get negative 1 minus 7 is negative 8. I see dividing by 4 in order here. Again, I go for division. You might go for multiplication. I want you to see division as often as you kind of can there. And that becomes x minus y equals negative 2. Now look at these two equations here and there. So negative x and x, y and negative y, 2 and negative 2. So negative x plus x is 0, y minus y is 0, and 2 minus 2 is 0. 0 equals 0, infinitely many solutions. Now we're not done. What we need to do now is express one of these variables in terms of the other, and then we'll outright solve for z. We'll find a number that z represents after we do a substitution there, because the x's and y's, or the x's should cancel with y's. If I say take this top equation where y, I think y can be better solved here. Negative x plus y equals 2. I can add x to both sides, and I get y equals x plus 2. Okay? So now, when I write my ordered triple, I'm not done, but when I write my ordered triple, x will be its own, variable. Y will depend on x, like that, and then z is probably going to represent a number. Let's find out what z is by substituting x plus 2 in for y in any of the equations that still contains a z. Let's do maybe this one up top. X is still x. So x plus, and then 2 times x plus 2 minus z equals 3. So I have that written over here. X plus 2y minus z equals 3. X plus 2y minus z equals 3. Oh, the x's didn't cancel. I thought every time it would depend on that one, but I guess not. 3x plus 4 minus z equals 3. Okay, subtract 4 over, and subtract 3x over, I guess. Negative z equals negative 3x. 3 minus 4 is negative 1, so z equals 3x plus 1. So I suppose you can still have something in terms of x for the other thing as well. I thought it would always be a number. I guess I'm not too ingrained with the visual of 3D graphs. I'll be honest, I haven't seen 3D graphs since my freshman year of college, so I'm not even really sure what they'd look like for that as a whole. But yeah, everything in terms of x would be this, which is still fine. It just works a different way, and this is your system all dependent on x. If x is 5, this becomes 5, 7, and 16, things like that. There's an infinitely many solutions, it's just not all real numbers. Okay, let's go to numbers 15 and 16. We have x plus 2y plus 3z equals 4. I see what they're doing there. Look at that. 1x, 2y, 3z, 4. Whenever I'm a test writer or quiz writer for my students, I always try and do things that are fancy like that somewhere in a problem, as long as they still act cleanly. Sometimes I wonder how problem writers come up with some problems. It takes me a long time to come up with a good problem that still works cleanly enough. Now this one I anticipate no solution or infinitely many solutions. Which one would we like to eliminate? I see the y's as easy to eliminate because there's nothing I have to do multiplication of, assuming I do equations 1 and 3 and equations 2 and 3, because the 2y and negative 2y. They're setting us up for elimination here and now. So equations 1 and 3, x minus 2x is negative x, 2y minus 2y is 0, 3z minus 4z is negative z, 4 minus 14 is negative 10. For equations 2 and 3, negative 3x minus 2x is negative 5x, 2y minus 2y is 0, negative z minus 4z is negative 5z, 12 minus 14 is negative 2. Now, generally I'd do the whole divide by 5 thing here, but 2 can't divide by 5. So instead I'm going to take the top equation and multiply by 5, or rather, negative 5. So if I do that, I'll get 5x plus 5z equals 50. And now when I eliminate, you'll notice these go away and these go away, but the right side does not go away. And when I say go away, I mean become 0. So 0 equals, in this case, 48. Definitely not a true statement. All variables canceled. This is a no solution set. Back to the no solutions. Probably the fastest of the problems we're going to see here. And then lastly, number 16. Let's see, we've done 2 plus 1. We've done 3 no solutions. This will probably be an infinitely many solutions one more time. I'm good at predicting textbook behavior. Negative 2x minus 3y plus z equals negative 6. Maybe z's are in order. X plus y minus z equals 5. Oh, those z's could cancel. The z's here would take a little bit more work, but not much. So once again, before I go on solving the problem, I want to still talk about how I make goals and which variable to eliminate here. Why do I want to eliminate z? 2 reasons. Number 1 can already eliminate by adding straight up. Number 2, the second one I can eliminate comes by multiplying by a positive number. I can multiply this equation here by 6, and that'll eliminate with that one. If I want to eliminate x's, or y's, not only would I have to multiply by one set to get it eliminated, but to multiply by the other set to get eliminated, I have to multiply by a negative. It just takes more work. It leads to more, it sets you up for more possible error. Z's are best set up for this one. If I do equations 1 and 2, add them down together right now, I get negative x, negative 2y, z's are gone, and negative 1. Now I can take the top equation and multiply it by 6, times 6. Let's write that just below the third equation, if that's okay. And I get negative 12x minus 18y plus 6z equals negative 36. And now those z's can eliminate. So I didn't have to multiply by a negative. It already just does what it does. So now I have negative 5x minus 10y. A lot of negatives in this result, though. Z's are gone and equals negative 5. I could take the bottom equation and divide by negative 5 with all of them, and I get positive x plus 2y equals positive 1. You can see where this is going. X's cancel, y's cancel, 1's cancel, or rather they all become 0. You get 0 equals 0. This is an infinitely many solutions case, but we still have more to do, as you've seen before. What we now have to do is express one variable in terms of the other among y and x. Let's make a choice. I got on this one, for example, x plus 2y equals 1. I think x is easy to solve for here. X is negative 2y plus 1. Would rather say negative 2y plus 1 or 1 minus 2y. I'll say negative 2y plus 1. I like ordered standard form. Negative 2y plus 1 is one way I'm going to write that out. Now I use that to solve for y is going to be y, right? So as far as my ordered triple goes, I have negative 2y plus 1 for x in terms of y. Y is going to be y, and let's solve for z. Now, y might not cancel when I solve for z, as I've now recognized sillily. I should have known that from the jump. Let's do it on the second equation here. X plus y minus z. So x plus y minus z equals, right? This is equation 2. X plus y minus z equals x. Remember, x is that plus 1, 5. Yeah, I don't think y's cancel here. So negative 2y plus y is negative y. Subtract the 1 over here, you get 4. And divide by negative 1, z is negative y minus 4. So negative y minus 4. So the final answer is right here that I'm boxing like that. I hope you can see it all. So negative 2y plus 1, comma y, comma negative y minus 4 is my final set. Now, you may wonder, is there more than one way to write the answer? I suppose, right? I decided to solve for x in this equation by subtracting 2y. But what if I decided to solve for y by subtracting x and dividing by 2? Well, I could have. Then I would have written my answer in terms of x. And the same thing with z. Z would have been in terms of x. So there's nothing wrong with that. It would have been a fraction. So I guess there's more than one way you can write an answer based off that. That's the one that I chose. Okay, we're an hour and 20 in. Water hit. The Dark Knight is going to finish before this video finishes. It's my guess. It's about a 2.5 hour movie. Okay, number 17. I don't think I have room for binder paper stuff there, so let's move forward. Word problem. 3 orders are placed at a pizza shop. 2 small pizzas, a liter of soda, and a salad cost $14. one small pizza, a liter of soda, and 3 salads cost $15, and 3 small pizzas, a liter of soda, and 2 salads cost $22. How much does each item cost? I'm going to define variables here. I'm going to let x equal cost per pizza. Is it a slice? Just a small pizza. Cost per small pizza. You can tell that when they say how much does each cost and we don't have, we don't have things for them, we can define them. These are in dollars, I guess. Y is 1 liter of soda, cost per liter of soda. And then Z, hopefully there's no infinitely many solutions or no solution for this. Why? Oh, I thought this was, cost per salad. Cost per salad. Right? Pizza, soda, salad. Okay, so there are 3 different things set up here. It's kind of hard to get this one wrong when it comes to it. You got totals adding to $14, $15, and $22 by taking 2 small pizzas times the cost of each pizza plus 1 liter of soda times the cost of the liter of soda plus 1 salad times the cost of the salad. Boom, like that. So that's how we're working that out. 2 plus 1 plus 1. And then 1 small pizza plus 1 liter of soda plus 3 salads is $15. And then 3 small pizzas plus 1 liter of soda plus 2 salads is $22. This isn't a guess and check thing, right? I'm sure this seems like the things on Facebook when you have like 3 bananas plus 2 oranges plus 5 cherries equals this, and solve it. And you can do it as a system. Of course, the trick on those problems is, that bunch of bananas had 14 in them, and this one had 13. You idiot, you should have counted the number of bananas in the bunch. Like, oh my God. Anyway, let's solve for these ones here. Now, my version of this I want to do is probably eliminate y's. You'll notice everything here will be positive. We got to add them. I'm going to take a single equation, multiply by -1. I'm choosing the top one because it has the smallest of the other numbers. So if I multiply this by -1, then this will become -2x minus y minus z equals -14. And this y can now eliminate with equation 2 and with equation 3. Remember, this is equation 1 rewritten. So I can do equation 1 with 2. The new equation 1 is right here. So x minus 2x, y minus y, 3z minus z, 15 minus 14. Now I'll do equation 1 and equation 3. So right here, these two. 3x minus 2x, y minus y, 2z minus z, and 22 minus 14. All right, now in this system here, x's can eliminate. Just add down that list. 2z plus z and 1 plus 8. And it's refreshing to get back, because when was the last time we had a system where we had integer solutions like this? The last 6 problems were infinitely many or no solutions, and before that were crazy fraction answers. So this is good to see. So z equals 3. If z equals 3, x plus 3 equals 8, and x equals 5. Very nice. Suddenly these problems seem quicker again. And then y, maybe take this middle equation, x plus y plus 3z. X plus y plus 3z equals 15. Agreed? All right. So y plus 14 equals 15 and y equals 1. Now, as an ordered triple, this would be 5, 1, 3. However, it's a word problem. And I define these variables x, y, and z very specifically. Cost per small pizza, cost per liter of soda, cost per salad. These are all in dollars. Now, I'm not going to double check this. It all looks pretty good. But I'm going to write this out. Each small pizza costs, boom. Each liter of soda costs, boom. Each small pizza costs $5. Each small salad, no, small salad? Is it salad? Each liter of soda costs $1. And each salad costs $3. That is the final result you want to put for an ordered, instead of an ordered triple for a word problem. Context, sentences, words. All right. Okay, number 18. Probably another setup and solve. Sam's Furniture Store. Is that real? I feel like that's real. I don't furniture shop. I feel like that's a real name. Anyway, Sam's Furniture Store places the following advertisement in the local newspaper. Write a system of equations for the 3 combinations of furniture. What is the price of each piece of furniture? Explain. Okay, if I'm going to define variables, I'm going to type them this time. So I'm going to let x equal, let's see what they have. $1,300 for a sofa and love seat, $1,400 for a sofa and 2 chairs, $1,600 for a sofa, love seat, and 1 chair. Looks like sofa should be first. Cost per sofa in buckaroos. I'm going to just get that copied and pasted, ready to go. Y is going to be cost per, what was next? A love seat. Cost per love seat. And then Z is cost per chair. So that setup will get me going with this here. I will do 1 sofa and 1 love seat is 1,300. I'm going to leave space because I want some equations that will use Z. 1 sofa and 2 chairs. That'll be 2Z. Now this might look weird to you with the spacing, but it will probably help you. Let me put the plus not here though. Let me put it where the 2Z is. X plus 2Z equals 1,400. And then a sofa, a love seat, and 1 chair there. So you can see where the spacing probably makes more sense for what we're doing, right? It lets you see what's kind of there and what's not. What do you want to do in a situation like this when you have a variable alone here and here? It's a good question. Suddenly I'm trying to think of what I want to do. Let's just eliminate the easiest variable to get rid of. Actually, solving for Z straight up is something I can do. This is one of the easier ones you can do once you find your strategy. I want to take the top equation and multiply by -1. I'm going to right now eliminate just X and Y straight up. Both of them. Kill 2 birds with 1 stone. As my high school AS chemistry teacher, honors chemistry teacher, Mr. Guzman would say, you kill 2 birds with 1 stone. He said it all the time. I loved it. He's a great teacher. He's still teaching there, I believe. So Z is 300, and I'm on the brink of turning 36. So over 20 years ago, he was teaching there. I think he still is. He's awesome. Z is 300. Those cancel out. Boom, boom, and there it is. That's it, right? I'm not done. But now I can use that to solve for X. And look, the second equation can be used there. And this is where you're being strategic. You can say, don't worry about eliminating Y or anything. I just substitute 300 in for Z right there. Just slide it in. Right? I know the cost for each chair. Now I can do it to find the cost of a sofa. X plus 600 equals 1,400. So X is 800. So Z is 300, X is 800. Now we use that to solve for either this equation or the bottom one. I'm going to use the top one again. X plus Y, a sofa plus a love seat equals 1,300. So Y is 500. So what's our final result there? I will not write the order triple. This time I'll just write the sentence. Each sofa, or 1 sofa, each sofa costs $800. Each love seat costs $500. And each chair costs $300. And I also want to see if this answer makes sense, not just like check the algebra here, but a sofa I think should cost more than a love seat, and a love seat should cost more than a chair. So I feel like those answers are also appropriate, not just because they're integers and such, but because the thing behind the problem, if they set it up right like that, and if Sam's Furniture knows how to charge prices, that's what we would do. All right, we got 10 problems to solve using the substitution method. Now, my hope, let's see, it's a strange hope. My hope is some of these are no solution or infinite number of solutions, that they're mixed within here. Maybe my wish will come true for that and go like, all right, play every problem as it is. Just be careful. Now, they do state substitution method. Here's the thing. We only saw substitution method together once on the word problem in the lecture portion. And if you didn't see it, you can go find it. It's example 4. They literally say, see example 4, because they're bringing that up because they use substitution there. Now, they use substitution for kind of a different, I should say for a different reason, for a different setup. Your equations weren't all in standard form like this. They did more like, see number 23 where it says like Z equals 5. Like that substitution's a lot easier. So when we get to a problem like that, I guess it'll help. But this problem here isn't really set up for substitution the same way. Now, what they did with substitution, I don't know if you noticed it, they got a variable by itself, and then they substituted that expression for that variable into another equation to get a system of 2, and then they used elimination after that, or whatever they wanted to after that. So here's what I'm looking at. There's only one variable here, only a single variable here where getting it by itself will not lead to fractions in the other things. Can you see it? It's this y. That y, if I get it by itself, I'm not going to multiply by anything. I'm going to add 2x to both sides, subtract 6z from both sides. I'll get y equals 2x minus 6z plus 1. This expression can now substitute for y in the other two equations. It can substitute right here, and it can substitute right here. And I have to forcefully do that. I have to take the next two equations, I have to forcefully plug them into there. So in equation 2, I'm rewriting equation 2, and it's going to be rewritten as 3x plus 2y plus 5z equals 16. By the way, there's more than one way to solve using substitution. This is the way the book kind of did it. This is a nice way. This is a way that leaves you with no fractions. I'm going to go ahead and kind of keep it going this way. Anyway, so 3x, now you can see this is an equation with only x's and z's. So 4x minus 12z plus 2 plus 5z equals 16. So I distributed 2. Now I'm going to combine like terms. 7x, negative 12z plus 5z is negative 7z. And subtract 2 over, and I get 14. I'm already looking to probably divide those things by 7, but we'll see what the other equation does. Now in equation 3, I'm going to have 7x plus 3y, 7x plus 3y minus 4z equals 11. Now I'm going to distribute 7x plus 6x minus 18z plus 3 minus 4z equals 11. Combine, I get 13x minus 22z, and subtract 3 over equals 8. Okay, it's apparent to me that because now I have my two equations for my system, right? I have this one and this one here. It's apparent to me that dividing by 7 is going to be among the things I'd probably like to do. So I'm going to take this equation here. I'm going to divide it by 7 because I got to do something with this one and that one and work it out. So I have now 1x minus 1z equals 2, and this equation is still 13x minus 22z equals 8. Now, I can solve using elimination, or I can continue on a substitution path. Let me continue on my substitution warpath just for the sake of this problem to keep reminding you of what substitution is all about and how this trickle-up thing will actually be kind of quick in solving the rest of the problem, ultimately. I know that seemed like a lot, and it kind of was, but hopefully finishing this off will be kind of nice. As far as substitution goes, check this out. I can get x by itself here pretty easily. Just add z over. And now I can substitute z plus 2. This will remind you of what substitution was like back with IM1 stuff. You take this is what I always used to say, and you take this expression, you take the z plus 2, and you shove it up your x. I don't know if I said it so emphatically, but there you go. You substitute for x. 13 times z plus 2 minus 22z equals 8. Okay, now we distribute. You get 13z plus 26 minus 22z equals 8. Now we're going to solve for z here. Let's see if it all cleans up. Otherwise, some big mistake happened. Negative 9z equals, and subtract 26 over, that's negative 18. So you get z equals 2. Okay, z equals 2. Here's where things go kind of fast at the end. And I know you're like, well, that's really slow. Now I get to substitute z for 2 right here to solve for x. X is 2 plus 2, which is 4. Right? Basically, because x is by itself, I don't have to solve for x. I just have to evaluate x. And same thing here. 2 and 4 can go in my equation where I solve for y. 2x minus 6z plus 1. 2x minus 6z plus 1. And it's straight up already, now you just evaluate. 8 minus 12, negative 4, plus 1, negative 3. So that's the fast part about this. I don't have to choose which equation to do. I don't have to get it by itself after. That part really speeds up at the end. I'd call this one a little more foolproof once you've gotten which variable thing to get by itself. Maybe. I don't know. Depends. Which one do I prefer? I mean, I prefer elimination personally, and I'm sure you guys do as well, but we got 9 more problems of substitution to do here. Now, I don't know. See, if these systems of 2 like this have a way of solving something using substitution like this easily without fractions, I'll keep doing that. in showing you the substitution stuff. Otherwise, I'll do elimination on the system of 2 when I feel like I need to, because the notes were fine doing that, right? They kind of did that in that set. They're like, all right, we'll do that there. So just kind of heads up. Sometimes I'll do it, sometimes I won't. But I'm going to start with substitution each time. Okay, number 20. X minus 6y minus 2z equals negative 8. You can see we can get that x by itself right now. And that might be the way to go about it. Now, keep in mind, I've already stated there's more than one way you can do substitution solving on these problems. Sometimes what you'd want to do, and I don't know, I'm looking at this problem and thinking maybe I can do it here. Sometimes what you want to do is get x by itself in 2 different equations. And then it can let you to get y, another variable by itself. But that's if you're very focused on always using substitution through the entirety of the problem with no elimination whatsoever. So I don't know if I'm set on doing that for each problem. Okay. Anyway, let's rewrite this equation here by getting x by itself. Let's add 6y to both sides, add 2z to both sides, and there's the minus 8 there. So this is going to substitute in for x in the other 2 equations. It's going to do it here, and it's going to do it here, okay? So equation 2 will be rewritten as, you got to be careful, there's a negative right there in front. So negative 6y plus 2z minus 8 plus 5y plus 3z equals 2. Let's see how this pans out. Negative 6y minus 2z plus 8, distribute the negative. All right, let's combine. Negative 6y plus 5y is negative 1y. Negative 2z plus 3z is positive 1z. And subtract 8 over and you get negative 6. So there's one of our equations where, oh, I can very easily get z by itself. Now, unless something lines up itself very easily to solve using elimination, I'll probably try substitution again. Okay, so let's do equation 3 now, and let's substitute here. I got 3 times x, that's 6y plus 2z minus 8, minus 2y minus 4z equals 18. Distribute, you have 18y plus 6z minus 24 minus 2y minus 4z equals 18. And combine 18y minus 2y is 16y, 6z minus 4z is 2z, add 24 to both sides, you get 42. All right, those numbers are relatively big. I can divide everything by 2 here, and I get 8y plus z equals 21. So check this out. Here's my new system I have now. I have negative y plus z equals negative 6 and 8y plus z equals 21. If you want a true, listen, elimination is valid for this, all that stuff. I'm going to still use substitution for the rest of this one. If you want a true blue substitute through kind of problem like this, I can get z by itself in both of these equations. That would be pretty nifty. And then I can set those 2 equations by themselves and solve for y. That's a really hardcore substitution version. I'm saying it's hard. I'm saying that that's really full on, we're substituting all the way. I get z by itself here, and I get z by itself here. And then I just set these 2 equal to each other, right? I set y minus 6 equal to, this is kind of scattered, equal to negative 8y plus 21. Now I just solve for y like that. So there are a lot of ways, right? I could have gotten z by itself, substituted right there, and then I'd be good. All that's fine. I'm just giving you any version of what you can do through substitution as, you know, like I said, this is my video. I can work strategies and methods and give you versions of what you might want to prefer down the line. This isn't for me. It's still for you. Add 8y to both sides. Add 6 to both sides. Divide both sides by 9. You get y equals 3. This is where we start to work up the pipeline very fast, though. For example, z is y minus 6. Well, 3 minus 6 is negative 3. And then x, I'm going to fit this right down here. I know it's a squeeze. I'm going to go down a little bit more, like that. X is, what is it? 6y plus 2z minus 8. You can see it also right here. The 6y plus 2z minus 8. 6 times 3 is 18. 2 times, I'm going to write it up here. 2 times z, 2 times negative 3 is negative 6 and negative 8. 18 minus 6 is 12, minus 8 is 4. So x is 4. So your ordered triple is going to be 4, 3, negative 3. And that was as substitution-y. Not as substitution-y as you can get, but not looking back when substitution was used, right? It was just a straight up grr substitution. All right, number 21. On number 21, we have x plus y plus z equals 4. Classic case of there's a lot that I can choose to get by itself here. It's really a my choice thing, depending on how I want to work it. 5x plus, 5y, I already see where this is going, plus 5z equals 12. But here's the thing about this problem, right? We got to use substitution method. We can't use elimination method, at least not to start with. I'm looking at the top two equations and I'm seeing what kind of solution set thing this will be early on, so I'm just going to work off of that. We'll see how much work you have to do as an overall to make it be that, though. Let's just get x by itself here. You know, I really don't have a preference when it looks like, yeah. Let's just get x by itself here, and you'll get x equals negative y minus z plus 4. Now when I substitute this for x in this equation right here, I'm going to get 5 times negative y minus z plus 4 plus 5y plus 5z equals 12. And you'll see what happens. Negative 5y minus 5z plus 20 plus 5y plus 5z equals 12. Don't be one of those. Are those 5s or s's? Come on, guys. What have I written in s so far? Even when it had said sofa and soda and salad, you notice I used x and y, right? I'm not going to use x's. Negative 5y plus 5y is 0. Those are gone. Negative 5z plus 5z is 0. Those are gone. And you get 20 equals 12. I don't even have to subtract that over. I get 20 equals 12, which is not a true statement. Guys, this is a no solution case. Notice your variables canceled and the left side doesn't equal the right side. Now, would have the third equation done something with the other two equations and made some solution cases? I suppose, but we wouldn't be done with it, and these are inconsistent with each other. So that gives you a no solution case through substitution. A little wonkier, but you might have noticed right here, these are 5 times bigger, 5 times bigger, 5 times bigger, not 5 times bigger, and that's what I noticed. So, do I substitute this in the third equation? No, I'm done. I got no solution. I got no solution. Number 22. X plus 2y equals negative 1. Good start. No z. X plus 2y equals negative 1. Let me give some space there. Let me do that again. And then negative x plus 3y plus 2z equals negative 4, and negative x plus y minus 4z equals 10. Okay, I'm looking at that top equation and saying let's get x by itself in that one as well. X equals negative 2y minus 1, and I can substitute now into both of these other equations, and it'll work like the other ones that we did. It's just now there's no z I got to combine things with. So now I'm going to substitute negative 2y minus 1 right here and right here. And I think I'm going to go without the parentheses bit. Notice this shows negative x. The opposite of negative 2y minus 1 is 2y plus 1. You follow me on that? When I do that substitution, the opposite of negative 2y minus 1, distribute the negative, I get 2y plus 1. That'll go a little bit faster. Then plus 3y plus 2z equals negative 4. Combine here, 5y plus 2z equals, subtract 1, negative 5. So there's equation 2. Equation 3, same thing. I get 2y plus 1, because you distribute the negative, plus y minus 4z equals 10. 2y plus y is 3y. I have minus 4z, and subtract 1 over, you get 9. So these are my two equations here and here. This is one where, and I'm going to rewrite them, 5y plus 2z equals negative 5, and 3y minus 4z equals 9. This is one where not only can I not divide by anything here to clean it up, that also goes to say that I can't get a variable by itself without being a fraction. So I'm not going to use substitution here on out the rest of the way. I'm going to use elimination on this one this time. And it's fine. They'll let me do that here. I used substitution right there. That was the substitution action onto this guy here and onto this guy here, right? When I distribute the negative and all that. Now elimination can take hold on the system of 2. That's fine. And for me to use elimination, I'm going to multiply the top equation by negative 2. That'll eliminate my z's. No, by positive 2, excuse me. Times 2. That'll eliminate my z's. So 10y plus 4z equals negative 10. And now I'm going to get 13y equals negative 1. So y is negative 1/13. Assuming all went well, then that would be that portion of the solution there, right? So negative 1/13 is y. Now I'm going to use that. When I said I'd get fractions with substitution, that didn't guarantee you'd get fraction answers. This was a fraction answer regardless. Now that I got negative 1/13 for y, let's plug it in and solve for z. Let's maybe take that top equation again. We get 5y plus 2z equals, was this the one that had, I can also solve for x using the same y up there, okay? So anyway, I'm going to solve for z here. 5y plus 2z equals negative 5. You know I'm going to multiply by negative 13 at some point here. Negative 5/13 plus 2z equals negative 5. All right, let's multiply let's multiply both sides by 13. And let's get negative 5 plus 26z equals negative 65. Add 5 to both sides and divide both sides by 26. This is one of those ones where they really like when you divide by 13 once, you divide by 13 the whole time, don't you? They really like that in these problems. But negative 30/13 is that one. Now, x, if you recall, x was negative 2y minus 1. So I'm bringing that back. X equals negative 2y minus 1. Whoops. This time I'm not going to go for multiply both sides by 13 or anything like that. This time I'm just going to chase the common denominator. X is 2/13 minus 1. Now 1 is also 13/13. That's where the common denominator comes in. So x is negative 11 over 13. So all these are one of those over 13 kinds of problems. We've got negative 11/13, negative 1/13, and negative 30/13. I'm trusting that's the right answer as far as I'm trusting my own work. We've seen fraction answers before. And I didn't mention this for the previous problem, but the previous problem was a no solution. So it's nice to see that no solution is a mix, it falls into the mix here. So 22 started way up here, finished way down there. Obviously, I have less room to write on binder paper than you guys probably do, but hopefully that's well enough organized that you had that taken care of. How far in are we? Whoa, almost 2 hours. All right. Not even really halfway through. Number 23. Let's see if I have enough room on my computer. That's the concern. I'll be honest. I might have a computer space issue eventually. We'll see. Number 23. We got 2x minus 3y plus z equals 10. Ooh, this problem should be fast. Y plus, this is a fun problem. It's a trickle up problem. You'll see what I mean. Z equals 5. All right, z equals 5. That's literally what z is, right? That's one of the answers. Now you can substitute for that. Take this equation, second equation, substitute 5. 2 times 5 is 10. So y is 3. And then take both of those and trickle that one up into this bottom equation right here to solve for x. 2x minus 3y, that's 9, plus 5 equals 10. 2x minus 4 equals 10. It's good to get a problem like this here and there. 2x equals 14, so x equals 7. And you might say, wait, Mr. Robinson, you never used substitution on this problem. Yeah, we did. Z is 5. We substituted 5 for z. It's right there. It's already by itself. The method is a goal to get variables by themselves to get down to a system of 2. We didn't need to do that here. One of the equations, one of the variables was already solved for. So, we're good there. Substitution method, done. This number's the same, only it's more of a trickle down than a trickle up, but number 24. Take a look at this. I'll take more of these, please. X equals 4. Looks like we don't get any more after this in any sort of way. I'm just going to write it. Hold on, I just had it. Fine. But I'm going to write x equals 4 just like that. I'll write the spacing exactly as they have. See if you're okay with the appearance of clutter. 4x minus 3y plus 2z. I was expecting it to say 1 equals 26. All right, if x equals 4, we can substitute into this equation here. 4 plus y is negative 6, so y is negative 10. So x is 4, by the way. And then for z, we got 4 times 4 plus, because negative 3 times negative 10 is 30, plus 2z equals 26. Subtract 46, you get 2z equals negative 20, divide by 2, you get z equals negative 10. Don't know why I color-coded this time, but 4, negative 10, negative 10 is the solution to this system here for x, y, and z as an ordered triple, right? Okay, number 25. Probably back to conventional substitution practices. Okay. Number 25. X plus y. I should do some ASMR for this one. 3x plus 2y plus 4z equals 17. I hope you're a headphone user right now. You can turn it on. Let's see how this sounds. I don't know how to do ASMR stuff at all. Okay, I'm going to speak a little bit louder here. Get ready for your headphones to kind of get back to normal. Okay, ready? So I got the problem written. Here we go. Now we got to use elimination for this. Same thing as getting a variable by itself. There's no reason I shouldn't kind of stick with the x trend here. Maybe I should. You know what? Z, let's do this time. I'm going to get z by itself in the top equation. Now what it's going to do, it's going to take 2 steps to get there, right? Unless you know what's going to happen. How about this? I add z to both sides and subtract 4 from both sides. Z equals x plus y minus 4. Now, the reason I do that is just because, listen, if I get x by itself here, y will turn negative, and I then have to distribute a negative into things when it comes to that. So why don't we do one where z here is already by itself on that, and the x and y's are positive here? Why not just make it a little nicer? I don't know. It's just a different kind of strategy. Anyway, let's look at equations 2 and 3. We're going to have to do substitution of this for z. So this one, 3x plus 2y plus 4z equals 17. So we get 3x plus 2y plus 4x plus 4y minus 56 equals 17. That's 7x combined, 6y combined, and add 56 over, you get 73. So there's an equation, equation 2. Equation 3, negative x plus 5y plus z. Z is x plus y minus 14. Was it 14? It wasn't 14. It was 4. Hold on a second. Let's go back. I made a mistake. That's a 4. So this is 16. I'm very sorry. That's 16. I add 16 over. I get 33. I don't know what happened there. I'm like, I don't remember that being 14. Negative x plus 5y plus z. So that's x plus y minus 4. Okay, I think we're addressed now. And that equals 8. So I'm taking the bottom equation here, rewriting it, but instead of z, I'm writing that. Negative x plus x is 0, so those are actually gone, which is nice. I can actually solve for y without using a system here. So still a quicker problem. 6y equals, add 4, 12. You get y equals 2. So now that I got y equals 2, I can trickle up a little bit. This can still be treated within the system, and I have x and y by themselves here. So I can substitute in y right there. I'll get 7x plus 6y equals 33. The proper number it's supposed to be. Equals 33. 7x equals 21. And x equals 3. X is 3, y is 2. That'd be cool if z was 1. 3, 2, 1. All right, where's z? Let's use that one. X plus y minus 4. Z equals x plus y minus 4. Ha! 5 minus 4 is 1. They knew what they were doing. This is 3, 2, 1. Hey! All right. We're good. We're good. All right, that is number 25. So that still had a bit of ease because we didn't actually have to solve the system of 2 using a method. Y got by itself when the x is canceled. And I don't know if things would have been better by getting x by itself and substituting or not, but that seemed to be pretty okay. Okay, number 26. Did you like the ASMR? Tell me yes or no in the comments. Whenever I set up a long problem, I can ASMR for you guys the whole time. If you didn't, I shall not proceed with that. Okay. Do you have a preference of which one to get by itself here, Mr. Robinson? Let's see. It's going to either be this x or this y or this z. Anything else would leave me with fractions. Now, any one of them that I do is going to have to deal with the negative aspect of it. Which one would be best through substitution afterward? I guess a z. So let's get this z by itself, or this x. Either get this x by itself or that z. Let's get this z by itself. Let's do kind of the same thing as before. Add z over and subtract 15 over. So that'll be 2x minus y minus 15. It's still kind of a one step to me. I don't have to write two different actions for it. So 2x minus y minus 15 is going to go in right there and right there in both of these equations. I'll just write these now in black. I hope you're okay with that. So equation 2 is going to be rewritten as 4x plus 5y plus 2z. Let's make sure I write the equation right this time. And 4x plus 5y plus, distribute the 2. In combined like terms, 4x plus 4x, 5y minus 2y, add 30 to both sides, you get 40. All right, there's an equation. Let's now go to equation 3 and write that as negative x minus 4y plus 3z equals negative 20. Okay? So that's negative x minus 4y plus 6x minus 3y minus 45 equals negative 20. Substitution's not bad. I do think it's longer, though. Negative x plus 6x is 5x. Negative 4y minus 3y is negative 7y. Add 45 to both sides and you get 25. And, I'll be honest. Like I said, there are multiple forms of substitution. Some is substitution the whole way through, and not even the way that I did it, but just a forcefully substitution at all costs of fractions and such. That's the one that I mostly dislike, and other people are kind of gluing themselves to. I know the book doesn't really call substitution that way, but whoop, there it is. This one is something I'm going to solve the rest of the way using elimination, but it's not still set up very pretty, even in the system of 2. This is one of the harder problems in IM1 solving a system 2 that you would have, because there's nothing that can divide to clean it up, although you generally wouldn't see that. There's no... Why did I write y's everywhere? What did I just do? These are supposed to be x's. Give me 1 second. These are supposed to be x's here. Anyway, these, in the system of 2, there's no one thing that's easiest to solve for here. You know what I mean? You can't multiply by a single number to get it by itself, yada, yada. Now, I'm going to choose to eliminate y's. There are 2 reasons I'm going to do that. Number 1... 3 and 7 have a smaller least common multiple than 8 and 5. This least common multiple is 21. This least common multiple is 40, which means probably bigger numbers have to multiply for that. Number 2, one's already positive, one's already negative. I think it's best that when you do this thing here, you deal with that when you can. So I'm going to multiply this whole thing by 7. I'm going to multiply this whole thing by 3, and we'll see what it looks like. We got 56x plus 21y. So I'm using elimination now, right? Equals 280. And here I get 15x minus 21y equals 75. Add down the list, I get 81x. I get 71x equals 355. Divide by 71. You can bet that number's 5. These canceled out, by the way. That being said, I can substitute 5 into x for one of these and solve for y. Let's take the top equation and maybe rewrite that one. That's 8x plus 3y equals 40. That's 40 plus 3y equals 40. So 3y equals 0 or y equals 0. Now that x is 5 and y is 0, we can use it to solve for z, and we have this equation to solve for z with 2x minus y minus 15. Z, whoops, what happened? Z is 2x minus y minus 15, and that's 10 minus 15, which is negative 5. So we get 5, 0, and negative 5. Oh, that one's cool too, because it has some symmetry and it's just subtracting numbers and such and such. And that's the final solution for number 26. 2 more, 27 and 28. I assume an infinite number of solutions has to come up somewhere here, as well as maybe another fraction answer or something. They have to, make some things happen in the last 2 problems, right? So number 27, we got 4x plus y plus 5z equals 5. Oh, yeah. Now that I look at this one, this is probably an infinite solutions one. 8x plus 2y plus 10z. I'm just going to bring this up and just not hide the fact of what I see here. I want you to see it with me. You see in the top two equations, you see how this is double, you know, times 2, times 2, times 2, times 2, right? That's where the 0 equals 0 case comes into play. There's still more I have to do when it comes to solving, right? But I just want to kind of bring that to light right now. Now, as far as doing something here, I'm going to get this y by itself in this equation by subtracting 4x. Now, you might say, actually, you know what? Let's do this. Let's do this. Let's take this equation, get x by itself. I don't automatically have to get the infinite solutions part. Let's just get x by itself here. Get x equal y plus 2z minus 2. And let's, when we plug it into here, maybe that part will reveal itself when we solve that portion of the system. And I have all positive numbers there, which is nice. So let's take equation 1, equation 2, substitute those x's into it. And the thing that I feel like, see, this is where I get kind of like, I want to divide this equation by 2 already, but then it's just going to become this equation up top. So I don't know. I'm going to suffer with a little more work than less in doing what I'm about to do. So this will be 4x from equation 1, 4x plus y plus 5z equals 5, 4y plus 8z minus 8 plus y plus 5z equals 5. Okay, I'll solve in silence here. Okay. So I combined the y's, combined the z's, added 8 over. Now in the next equation, equation number 2, I'm going to do the same thing. Everything's twice as big as this equation though. So I expect to get 10y plus 26z equals 26, just so you know. All right, so 8 is going to distribute into y plus 2z minus 2. Let me operate in silence after I write this one out right here from equation 2. Okay, here we go. And add that's 26. Okay. Okay. Yeah, 10y plus 26z equals 26. So if you notice now, which we can use elimination here on out if you'd like to, this is literally still half of that. So if I'm truly going to use elimination method the way that I would is I'd take this equation, multiply by -2, and you get negative 10y minus 26z equals negative 26. And then everything kind of cancels out, right? So you get 0 equals 0, which leads to your infinite number of solutions. But we're not done at that case because we still have to express, or infinitely many solutions, I should say. Infinitely many solutions. What I would do in this case here, generally, is now get one of these two variables by itself, y or z, in terms of the other, one in terms of the other. And then we got to solve for x with that. Now, the problem is you're still going to have fractions within here. This is almost a real case of substitution. Let's get, I don't know, do you want to get y or z by itself? Let's get y by itself. It's a smaller number, I guess, to divide by. And I don't know. So if I get y by itself on that top equation, 5y plus 13z equals 13. I'll subtract 13z from both sides. So we'll get 5y equals negative 13z plus 13. Right? Those are the numbers? Okay. And then I'll divide both sides by 5. So now I'll get y equals, let's just write it all over 5. Negative 13z plus 13 all over 5. So remember, as far as my ordered triple goes, z is going to be z. Y is going to be negative 13z plus 13 over 5. Remember when I said I anticipate these last answers to have either infinitely many solutions or fractions? This said both. So we still have to solve for x. Okay? We have to take my equation. We'll take the equation where x is by itself, this one, y plus 2z minus 2. This is our first infinitely many solutions where that thing's solved for here. So x is y plus 2z minus 2. X, I'll write it in a different color. X equals y plus 2z minus 2. Let's get a common denominator here. So 2z will turn into 10z over 5, and 2 will turn into 10 over 5, plus 2z minus 2. So now that I got a common denominator, that'll be x equals, so they're all over 5, right? Negative 13z plus 10z is negative 3z. 13 minus 10 is 3, and this is all over 5. So that's x's solution there. I know that my thing is breaking now that I'm going to this much of the screen. I didn't expect to go this low. So x is also in terms of z there. Negative 3z plus 3 all over 5. I mean, only hoping that's the right answer in play, but with that said, that would be my ordered triple with that one there. Really crazy looking, and I did it in terms of z, but there we have it. Negative 3z plus 3 over 5 is x. Negative 13z plus 13 over 5 is y, and z is z. Okay, last one, number 28. Not the last problem of the set. In fact, we'd still have like 15 more problems to go after this. Kind of late on my end. All right, number 28. X. I don't know what to expect for this kind of answer. Hopefully it's clean. Maybe they're like, we'll finish you with a softy. Nope, this looks like another. You see what this looks like? Anyone see the two top equations? Double this, double that. Oh, look at the third equation. Oh, I don't know what to get on this one. All right, prepare yourselves. Something's coming and I don't know what. Okay, let's get the bottom equation by itself for z. That'll be straightforward as far as things go. That'll be z equals, oh, that's a negative 6 though. Okay, that's going to change some things up. Z is x plus 2y minus 6. All right, let's substitute those into these two equations and just see what happens, right? Whatever happens, happens. So in equation 1, we'll get x plus 2y minus, minus z equals 3. Now that's x plus 2y, distribute that, negative x, negative 2y, and plus 6. Okay, so this will take care of itself pretty fast then. X minus x is 0. 2y minus 2y is 0. And you get 6 equals 3. As a result, that'll be a no solution case. You'll be done there. A lot of things could have happened here. I don't know. See, if I used the top two equations, I would have gotten infinitely many solutions, but then you would have found out something would have broke down in the third equation, so it actually would have been a no solution case. You would have said infinitely many solutions, but that's just for those two. That's just for those two planes together. Those are infinitely many, but then they end up not intersecting with the third one. So what this really is this problem has two planes intersecting with each other everywhere, and then a third plane, which I don't know how to draw the planes here, but a third plane is parallel to those two planes. So this plane, another plane, and then a third plane is right there. So these two intersect everywhere together. That one doesn't anywhere. That was equation 3. Okay, so that's the last one on no solution, or substitution. That's a no solution one. Interesting, kind of different answer. All right, let's go to number 29. Ooh, hands. The number of left-handed people in the world is 1/10 the number of right-handed people. The percent of right-handed people is 9 times the percent of left-handed people and ambidextrous people combined. Ooh, what percent of people are ambidextrous? Okay. Is our answer in percentages of people or percents? I'll say percents. Let's let x equal percent of left-handed people. Y equal percent of right-handed people. I assume ambidextrous are their own thing, considering these are systems of 3. Z is percent of ambidextrous people. Okay, and I think these are in percentages that we do them. The number of left-handed people is 1/10 the number of right-handed people. If I don't want a fraction here, I'm going to multiply both sides by 10 and say 10x equals y, okay? Y equals 10x is another way I can say that. This is a substitution case I can use here. The percent of right-handed people, this is a percent, but I can still say number of and percent work the same way, right? Percent of left-handed people is 1/10%. Anyway, the percent of right-handed people is 9 times the percent of left-handed people and ambidextrous people combined. When you combine the number of left-handed and ambidextrous and make 9 times it, that's how many right-handed people there are. So this is my system. Now I also have 10x equals y, or y equals 10x. So I can substitute 10x into there. It says what percent of people are ambidextrous. I feel like I'm missing information. Number of left-handed people is 1/10 the number of right-handed. Percent of right-handed people is 9/10% of left-handed and ambidextrous. I'm missing something there. I have now 10x equals 9x plus 9z. And I have x equals 9z. The problem is I have two equations, right? I don't have three. The number of left-handed people in the world is 1/10 the number of right-handed people. Percent of right-handed people? Oh, I could probably just do this. What percent of people are ambidextrous? Oh, but it's still not a. It's still a system of. Oh, and x plus y plus z is 100. X plus the percent of all of them, right? X. Here's what I'm missing. X plus y plus z is 100. Should I say 100 or 1? I'll say 100. That's okay. We'll know our answer is in percent. If the answer is 40, I'll say 40%. Okay. Cool. Now, did I do things that I wanted to do here, or should I change it now? If x is 9z, 10x equals y. Okay, let's do this. I'm gonna reconfigure some of this a little bit. I'm like, I should have a third equation. So that's my third equation. Will this delete green? Awesome. Okay, I'm going to shuffle this a little bit. First of all, 10x equals y is how I'm going to just rewrite that whole middle equation. I just prefer or y equals 10x rather. You know what I mean. Y equals 10x. Okay. And I'm going to get rid of this bottom part for now unless I feel I want to use it. I want to see what I want to do here. Okay, let's take the y equals 10x and let's substitute 10x for y in both of these equations, up top and on bottom, and then we'll do something off of that, okay? So on the top equation, equation 1, I have x plus 10x plus z equals 100. So 11x plus z equals 100. Okay. And in the bottom equation, equation 3, I have 10x equals 9x plus 9z. I already had this before, but that's okay. Now I can write x equals 9z. Okay. If x equals 9z, now I guess I had that before, but now I can substitute 9z in for x right here, and I can solve for z, which is really what I want. What percent of people are ambidextrous? So 11 times 9z plus z equals 100. Oh, I thought this was going to be 0. So 100 z equals, 0% of people are ambidextrous. So z equals 1. 1% of people, that's all they wanted. They didn't want the percentages of the others. I assume the others are like, whatever, 9% and 90, whatever. 90%. Yeah, 90%, 9%, and 1%. So 1% of the world's population is ambidextrous. Not amphibious. Okay? Ambidextrous. Ambidextrous. All right. Number 30. Use a system. Yeah, so that's where, sorry, just going back to the previous problem one more time there. That's where you need 3 equations in a system of 3 to solve it. And that's where I was sitting there going like, what's the third equation? All right, number 30, modeling with mathematics. Use a system of linear equations to model the data in the following newspaper article. Solve the system to find how many athletes finished in each place. Lawrence High School prevailed in Saturday's track meet with the help of 20 individual event placers, earning a combined 68 points. Okay. A first place finish earns 5 points. A second place finish earns 3 points, and a third place finish earns 1 point. Lawrence had a strong second place showing with as many second place finishers as first place and third place finishers combined. Okay. First, second, third. Okay, second starts with an S. I'm not going to use that. I'm still going to use X, Y, and Z. Let X equal number. Is it number of first place finishers? Number of first place finishers. Y was number of second place finishers. and Z is number of third place finishers. Okay. All right, the first equation I can really do is just how many people there were total. They said 20 individual event placers. So there are this many first place finishers, this many second place finishers, this many third place finishers, which is 20 total event placers. Now, on a point scale, if you are first place person, you earn 5 points. So 5x is the number of points all first place people earned. 3 points per second place times the number of second place, and 1 point per third times the number of third, and that's 68 total. Somewhere there's got to be a third equation, which has to do with this sentence here. Lawrence had a strong second place showing with as many second place finishers as first and third place finishers combined. So the number of second place finishers equals the combined number of first and third, like that. So that's my system of 3 that we're going to solve for. And I feel like this is set up to be more substitution. So was number 29, because word came from the substitution set. So here, this is set up for substitution. Let's let x plus 3 take the place of y right here and right here. And then let's continue on that. No reason not to, right? So let's get that in equation 1. We're going to rewrite it, say x plus y plus z equals 20. That's pretty straightforward. That's 2x plus 2z equals 20. You know I want to divide that all by 2. X plus z equals 10. We'll see if I go more with that on substitution in a bit. And then here on equation 2, let's see if I can fit it here. I can't. Nope. Equation 2, 5x plus 3y, plus z equals 68. And that is 5x plus 3x plus 3z plus z equals 68. Okay. 8x plus 4z equals 68. You know what I want to do here? Divide everything by, I think, 4. 2x plus z equals 17. Okay. So we have a system of 2. X plus z equals 10. 2x plus z equals 17. You know, I could get z by itself here. And I could get z by itself here. And I could use those to solve for x by setting those equal to each other. 10 minus x equals 17 minus 2x. All right. Add 2x to both sides. Subtract 10 from both sides. X equals 7. All right. Everything substitution. Now we'll solve for z. Z is 10 minus 7. Z is 3. Now we'll solve for y. Y is x plus z. Y is 10. So see how fast substitution goes at the end after that? I always like how that kind of works out. There are as many second place finishers as there were first and third combined. 20 total. And apparently that score is 68. So how do we write that? There are 7 first place finishers, 10 second place finishers, and 3 third place finishers. That is our final result. All right, I've been going for a moment here. Let me give myself a little pause to refill my drink. Give me 1 second. All right, so meanwhile, I saw The Dark Knight was close to ending, so before it finished up and went on something random on HBO, I just went midway through the movie again here. Okay, let's see. We finished number 30. Let's keep going forward. What are we going to? 43. All right, 13 more problems. Number 31. I still got room down here. Explain when it might be more convenient to use the elimination method than the substitution method to solve a system. Give an example to support your claim. You know, substitution method seemed very fair for a problem like this, right? Variable is already by itself. Other problems, I don't know what you felt has been better or worse. I'd say most people would vote elimination if I made a poll. Most people would, but elimination seems to serve best. Elimination serves best when your equations are in standard form, or so to speak, especially if you can't get isolate a variable without having fractions, without inducing fractions. So, you know, imagine that you were only stuck with equations like, oh, let me find one. Imagine if you were only stuck with equations like this middle one right here. And in this middle one, if I solved for x, y, or z, I'd have to divide by a 4, 5, or 2 that would not cleanly divide by my other numbers possibly somewhere. I'd only have fractions. That's one where I'm really looking at elimination to do, unless you have a variable somewhere that you can get it. And it's likely they're going to give you a problem that does. Because then otherwise I have to work off those fractions for substitution. That doesn't mean the elimination will be easier. You still might get big numbers, but none of us really like fractions, and I think that's a case for that. So a good example of that will be this. They said, give an example. So my example here, I kind of just was pointing one out, but let's do something like 3x plus 2y minus 4z equals 7. Nothing there can easily get eliminated or get isolated by itself, right? 5x minus 6y plus 2z equals 1, and negative 2x plus 10y plus 5z equals 3, right? Nothing here can I get, it's in standard form, and nothing here can I do to get a variable by itself for elimination's sake and make it work in a very clean way to me, personally. The way that we would have to get y equals x equals something like that. Now, elimination is not necessarily any fun either. I would probably eliminate y. I'd probably multiply the top equation by 3 and the bottom in the top equation by negative 5 with, to eliminate on the y's here. But it's just, otherwise outside of that, it's whatever. So I just made that up, but that's kind of what I'm looking at. Now, I don't know if that supports it to you as far as what I'm doing there, but it makes sense to me. Okay, number 32. Using what you know about solving linear systems in 2 and 3 variables, plan a strategy for how you would solve a system that has 4 linear equations in 4 variables. Well, it says plan a strategy. Okay, so you can probably write the plan the same way as they did in the notes thing, which is step 1, step 2, whatever. But we're not going to actually solve it. But imagine if you had 4 variables, you'd probably say w, x, y, and z. Okay, so step 1 is really this. Notice what we do. Let's work a trickle up for a second, right? Let's do this together. When you're doing a system of 2, when you're solving a system of 2, your goal is to get a variable by itself. You get it to a system of 1, if you will. So you turn a system of 2 into a system of 1. What we've been doing in this one for a system of 3, you got to get it to a system of 2 first before you turn it into a system of 1. So a system of 4, your first goal is to get into a system of 3. And then use the system of 3 to get into system of 2. So I don't know if I want to say step 1 and stuff, but my strategy is basically take my system of 4, and turn it into a system of 3. Take the system, eliminate, get rid of, eliminate, whatever. Eliminate a variable in your system of 4 in 3 separate equations to create a system of 3 equations with 3 variables. So let's say, how it might have w as one of your variables. Get rid of the w in those equations by using elimination method, whatever, or substitution method, same kind of thing. You can do it, substitute in the other 3 equations, and then get a system of 3 with x, y, and z, and then solve for those. Step 2, etc. Remaining steps, solve your system of 3, then substitute, so that's whatever, and then substitute those 3 variables into an original equation to solve your 4th variable. And then the last step, I should just mention this, final step, write final solution. Here, I shouldn't say remaining steps. Let's do this. Step 2, solve your system of 3, as we would, right? Step 3, sorry about that. Step 3, substitute, and then step 4, write final solution as an ordered quadruple. I guess that's what you call it. An ordered quartet, an ordered quadruple. I don't know what it's called. But that would be my step 4. That's my plan for that one. I've solved systems of 4, not very often. Never solved a system of 5. I don't care to, ever. Okay. Number 33. In exercises 33 and 34, write and use a linear system to answer the question. All right. The triangle has a perimeter of 65 feet What are the lengths of sides L, M, and N? So if I'm writing this as a system of 3, and substitution's kind of already there for you, but I could say L plus M plus N, that's the perimeter, equals 65. And then you have two other things here. You have L equals 1/3 M, and N equals L plus M minus 15. Kind of an interesting way of going about how they write it. Depends on how you want to solve it. But if N's already by itself there, and L already has something there, I suppose we can substitute this all into the top equation and just get M by itself. Well, let's do this. Substitute 1/3 M right there. So now you'll have N equals 1/3 M plus M minus 15. I know it's a fraction. I'll just deal with it for now, and then I'll take care of it later. 1/3 M plus M is 4/3 M. So now I can take this expression, substitute it in for N. Let's use a different color. I can take this expression, substitute it for N, take this expression, substitute it for L, and I'll have an equation with only M's in it. Okay, so L will be 1/3 M, then there's plus this M, and N will be 4/3 M minus 15. This isn't the only way to do the problem, but this seems most reasonable with, I guess, with what I have. If I combine, let's see, you want to multiply everything by 3 right now, I guess? Just get rid of the fractions now? I don't know if the answer will have fractions or not, but currently it does. Let's see, times, I thought I chose this blue. There we go. Times 3. So now I have M plus 3M plus 4M minus 45 equals, what is that? 195. So combine like terms, you get 8M. Add 45 over, you get 240. Divide by M, you get 30. So that's an example of, okay, that one's not a fraction. You had fractions, but it's not ultimately. M is 30. L is 1/3 of M. 1/3 of 30 is 10. And N is 4/3. See, I'm going to use this one. N is 4/3 of 30 minus 15. Actually, there was probably an easier one here. No, that's that's okay. 4/3 of 30 is 40, and 40 minus 15 is 25. Let's just make sure that 30 plus 10 plus 25 is 65. Yep. Okay. So this is feet. So let's write it one more time. L is 10 feet. I'm just boxing them again. M is 30 feet. N is 25 feet. Now, this is one where it's a word problem, so I'm not going to write an ordered triple for this thing. I could, but 10, 30, and 25 are for L, M, and N, like so. Okay, number 34. What are the measures of angles A, B, and C? 34. You have, I don't know if that's a right triangle. It doesn't show. Oh, I guess they want this. Like A is this guy right here, and measure of angle A is A degrees. I see. So A is A degrees. Oh, this will look weird. A is A. Sounds dumb. B is 5A minus, what did I just do? 5A minus C. And C is A plus B. A is a dumb equation. I'm not going to write that. What's my third equation going to be? It's a triangle. A plus B plus C is 180. Okay. Let's work off of that to solve our system. We can probably do the same thing as before. Which one should I substitute? This almost would be self-referential here. Let's substitute 5A minus C in for B right here. And then up here. So in the top equation, equation 1 will now look like A plus B plus C equals 180, or 6A. Oh, The c's cancel. 6a equals 180, so a equals 30. All right, well, I still got to solve for the others, but a is 30. 5a minus c will substitute here, so now I'll have equation 3 that says c equals a plus 5a minus c. C equals 6a minus, oh, I can add 2c equals 6a. Hold on a second. 2c equals 6a and c equals 3a. Oh, and a equals 30. So c equals 3 times 30, which is 90. I think these are degrees. Degrees. And b, now that we have 5a minus c is the thing. So b is 5a minus c. B is 150 minus 90, which is 60 degrees. I'll just leave them like that. We have them all there. If you can see where they are, c is 90 and all that. So those are our angles. We're all good to go on that. You know, I'm warming up to substitution when something's already by itself in that way, especially when we have a process. I'm not going to really use elimination unless we're actually in standard form. Okay, number 35 is open-ended. Consider the system of linear equations below. Choose non-zero values for a, b, and c so the system satisfies the given condition. Explain your reasoning. What? Oh, there are 3 parts. I didn't see the 3 parts. I'm like, what are you talking about? X plus y plus z equals 2. Hold on. A, B, C. Ax plus by plus cz equals 10. And then x minus 2y plus z equals 4. Okay, part A, we want the system has no solution. To have no solution, we're going to want to turn A, B, and C into, you could probably do 1. If you turn them all into 1, then they'll cancel with the top equation. I'm thinking elimination. They'll cancel with the top equation on these variables here, and 2 and 10 won't combine to equal 0. So if A equals 1, B equals 1, C equals 1. They say explain your reasoning. I'm going to show you. So if you do this, you take the first equation, x plus y plus z equals 2. The next equation is 1x plus 1y plus 1z equals 10. And I'll do this through subtraction. Normally I wouldn't, but these will all cancel, and 2 minus 10 is negative 8. So you get 0 equals negative 8. That's a no solution case. That's just kind of looking at how one sets up with the other and works it out. Now this was open-ended, so there's more than one answer to this, more than one way to do that, and that's just one form of what you can do. Obviously, you can make A, B, and C all be 3. It's still going to work out and give you no solution. But there are things you could probably line up with these ones to do the same thing. So there's part A, a no solution case. If A, B, and C equal 1, here's my explanation. All right, part B, the system has exactly 1 solution. I'll tell you what, it can probably be anything under the sun as long as it doesn't lead to any cancellation. So as long as these aren't like multiples of these numbers, I can like have A be 1, B be 2, and C be 3. They might not be good answers, but they might be fractions. But A equals 1, B equals 2, and C equals 3. I want to type out this justification. I'm not going to solve it. Basic justification is these coefficients do not share a similarity ratio or scale factor with any of the other coefficients corresponding to those variables in either of the other 2 equations. See, remember when I said on part A, I said there's more than one answer, and I said, listen, A was 1, B was 1, C was 1, because it went in correspondence with these. It let them cancel out. But A, B, and C could have also been 3, because as long as you go 3 times bigger, 3 times bigger, 3 times bigger, then those will still cancel out. And in a proper way here, these still wouldn't have been the same number to be no solution, but it's all about proportionality. It's all about correspondence, similarity ratio. So as long as 1, 2, and 3 don't go into the fold where everything's going to cancel together for this equation or this equation, then it will give you 1 solution. I mean, I believe so. I believe these ones won't work out to be no solution or infinite. Otherwise, something really messed up. Now, part C is the infinitely many solutions one, and that's where I have to be a little more clever. So infinitely, I had to write one solution for this. Give me 1 second. So infinitely many solutions. Excuse me. This one is one solution. One solution is here. Let's space this out a little bit more. Down, down, box it. Okay. Part C is infinitely many solutions. Now this is where I can try and be clever with that top equation as long as I get, I want A, B, and C to be numbers so that the 10 will cancel with it. So what would I have to multiply? See, I'd have to multiply 2 by 5 to be 10. And I understand normally I'd say negative 10, but that's all right. So I'd have to multiply these by 5 to be these numbers. I'd want A, B, and C in this case to be 5. If A, B, and C were 5, then these would be 5 times bigger, 5 times bigger, 5 times bigger, 5 times bigger. Everything would cancel and become 0. I'd get 0 equals 0. That's an infinitely many solutions case. And that's a good, easy example of one. A is 5, B is 5, C is 5. Every coefficient, every term, whatever, every term is 5 times larger than the top equation. So when eliminated, every variable and constant will become 0, making a true statement with canceled variables, like an infinite number of solutions case has. I'm not going to solve it, but that's just kind of the support that I have there. All right, that is my open-ended number 35. All right, number 36. Making an argument. Is this a your friend thing? A linear system in 3 variables has no solution. Your friend concludes it's not possible for 2 of the 3 equations to have any points in common. Is your friend correct? Explain your reasoning. Your friend is not correct. I think it's the 3rd time in a row your friend's not correct here. 2 of the 3 equations can have points in common, but not all 3 have points in common. So my friend, once again, is incorrect. I think that's at least 3 in a row. This whole, I think it's O for the chapter, maybe. My friend is incorrect. Once again, no, my friend is incorrect. 2 of the equations can have solutions together. Like, heck, on this one, if I just had this equation and this equation, ignore the second equation and, you know, whatever, these have solutions together. These planes intersect. They totally do. Heck, they can be the same equation and have infinitely many solutions. And that was like that last substitution problem in that set of 10. It was like, I don't know what number. But if not all, I guess this might be a weird sentence. If not all 3 equations share a common solution set, then it'll still be no solution. So we've run into several of those, I think, or we've at least had the idea of it. See, with no solution cases, when I had something cancel, I never bothered checking the other equations. I just stopped. But the other ones can have solution sets as long as x's and y's still merge together. They still will. But it's no solution as a system. So your friend, having trouble. All right, number 37 on problem solving. A contractor is hired to build an apartment complex. Each 840 square foot unit has a bedroom, kitchen, and bathroom. All right, so bedroom, bathroom, kitchen. Okay, the bedroom will be the same size as the kitchen. Okay. I don't know if it looks it, but I don't know if we're doing length times width stuff here. The owner orders 980 square foot of tile to completely cover the floors of 2 kitchens and 2 bathrooms. Determine how many square feet of carpet is needed for each bedroom. Okay, so this is not about amount. It's about carpet, but it's about square footing and area. So because some are tiles, some are carpets. So I'll just say square footing of each individual thing. We know the total is 840. I don't think we're doing length and width. We're just saying each part, bedroom, bathroom, kitchen. We'll use X, Y, and Z again. So let's let X equal area of bedroom in square feet. Y equal area of bathroom in square feet. and Z equal area of kitchen in square feet. I don't know if that's the order that they kind of said things, but I'll just write things from that. So every apartment is 840 square feet when you add the bedroom, bathroom, and kitchen. So that's one equation. A second equation, the bedroom will be the same size as the kitchen. A second equation will be bedroom is same size as kitchen. And a third equation said something about the carpets. Tiles. The owner orders 980 square feet of tile to completely cover the floor. There's 2 kitchens and 2 bathrooms. Bathrooms is Y, kitchens are Z. 2 kitchens plus 2 bathrooms is 980. Okay, I think this is our system of 3 we're going to go off of, all right? Now, x equals z is a pretty straightforward substitution here. I'm going to let z take x's place right there. And now we'll have z plus z, which is 2z. So I'm going to take this the top equation, and rewrite it on the bottom as y plus 2z. Whoopsie. Y plus 2z equals 840. Not only that, but I kind of want to take this equation and, well, you know, this kind of elimination right now. Let's just divide this equation by -2, and let's eliminate y. So we'll get negative y minus z equals negative 490. This will get us to solve for z immediately. Hopefully you're good on following my setup. This is more elimination after that first substitution. So 2z minus z is z, and 840 minus 490 is something. What's the answer we need, by the way? We need the bedroom. Well, x equals z, so that's nice. Whatever we solve for here should be the bedroom answer. 350? Z is 350. If z is 350, x is 350, because x equals z. So each bedroom needs 350 square feet of carpet. And so I assume the bathroom needs 140 square foot of, no. Yeah, 140 square foot of tiles. But we only need the bedroom answer. So each bedroom requires 350 square feet of carpet. All right. Yeah, once again, very open-ended. A lot of ways you can solve that one. That's the way I went about it. All right, number 38. What problem are we going to again? I keep forgetting. 43. So we got 6 more problems still. Thought-provoking. Does the system of linear equations have more than one solution? Justify your answer. Well, how about we solve it? Ooh. 4x plus y plus z equals 0. 2x plus 1/2 y minus 3z equals 0. Ooh, a lot of zeros. Negative x minus 1/4 y minus z equals 0. Okay. If you know me, you know that I won't want to deal with fractions. Let's just multiply this equation by 2 and see what it looks like. Let's multiply this equation by 4, see what it looks like. Let's get rid of those fractions as a whole. So let's rewrite this whole system one more time. 4x, I probably should have done it on this screen where it was written, equals 0. Multiply this by 2, we get 4x plus 1/2 y is 1y. Ooh, y, oh, minus 6z equals 0. Oh, interesting. Remember, 0 times anything is still 0, so these stay as zeros over here. 4 here is negative 4x. This is minus 1y minus 4z equals 0. All right, in an interesting kerfuffle, let's just combine equations 1 with 3 and 2 with 3, because we can eliminate right down the list there. So in equations 1 and 3, cancel, and z minus 4z is negative 3z. That equals 0, therefore z equals 0. You know what? Actually, I don't need to do what I said I was going to do there. I don't need to now combine these two to solve that z equals 0 once again. Let's just substitute. If z equals 0, let's get rid of these. Z equals 0 means nothing to me on this. Now we have this system. So look at the system now. Now the system says, and it doesn't matter which way you write it, 4x plus y equals 0, 4x plus y equals 0. We can ignore that. Now let's look at one of these, 4x minus 4x minus. You get 0 equals 0 in that case, but z also equals 0. So with these two, that's an infinitely many solutions. What did it ask? Does it have more than one solution? Yes. It has, it has infinitely many solutions. It didn't ask what the solution set is, so I'm going to stop right there. Remember, with infinitely many, we tend to write y. Actually, we're almost done. Y would be negative 4x. So I'd write my final system as x, negative 4x, and 0, like that. That's where I finish it. Y is based on x, whatever x is, y is whatever. But z is always 0. It has infinitely many. So does that have more than 1? Yes, it is infinitely. Okay, that's number 38. Number 39, problem solving. 3 parts. A florist must make 5 identical bridesmaids bouquets for a wedding. By the way, if you have trouble with word problems, trust me, I process slowly the same way. That's why I pause after sentences and go, okay, what did I just read? So we're making 5 identical bridesmaids bouquets. Okay, I don't know what to do with that number yet. I don't know what the question is. The budget is $160 and each bouquet must have 12 flowers. So when you combine all the flowers, I'm guessing there are 3 different sets of flowers, but when you combine all those flowers together, it equals 12. Where does the 5 go in? Bridesmaids bouquets. I don't. We'll see. Each bouquet must have 12 flowers. Oh, a bouquet is 12. 5 times 12. We'll see. The budget is 160. There's another combination there. Roses cost $2.50. I thought it said lilies cost $4 each, and irises cost $2 each. The florist wants twice as many roses as the other 2 types of flowers combined. Okay. Write a system of equations to represent this situation, assuming the florist plans to use the maximum budget, meaning kind of fill it all out. So first of all, they didn't ask a question yet, but it's number of roses, number of lilies, and number of irises. So let's go based off of that. Let's let x equal number of roses. Now, the only thing is I don't know if this is per bouquet. It says each bouquet must have 12 flowers. I don't know if we got to multiply by 5 yet or anything like that. That's the only thing that I'm having trouble with. I got to see what that's all about. I haven't read part B and C yet either. Y is number of lilies. Before I write the system, I'm going to read parts B and C. Z is number of irises. I named my car Iris. Okay. Write a system of equation represent the situation, assuming, okay. Part B, solve the system, find how many of each type of flower should be in each bouquet. All right. So the system is for every 1 bouquet. Part C, suppose there's no limitation on the total cost of the bouquets. Does the problem still have exactly 1 solution? If so, find the solution. Not get 3 possible. Oh, I see what they're saying. Okay. It's probably an infinitely many solutions thing, and then we get to arrange things, I think. Okay, this is for 1 bouquet. So number of roses per bouquet. All right? I think that's what we're doing there. So let's break this thing down. Write a system, solve the system. Part A, write the system. The budget is $160. Okay, each bouquet must have 12 flowers. X plus Y plus Z is 12. All right, the cost, $2.50, I'm right, 2.5, $2.50 per rose times the number of roses, plus $4 per lily times the number of lilies, plus $2 per iris times the number of irises is $160. Now, what I'm going to do with that one probably is multiply everything by 2, so this becomes a non-decimal. I'm just setting it up for now. The florist wants twice as many roses as the other 2 types of flowers combined. So another way of saying that sentence is the number of roses is twice the number of flowers of other types of flowers combined. So number of roses is twice the number. There's a car spinning out outside. I don't know if you hear the tires screeching. Number of other flowers combined, like that. So that's my system of 3 as a setup. All right. Let's go to part B, which is solving. Now, in terms of my solving, the first thing I'd like to do, actually, it's probably fine with this because these are 2s. When I double this, I think it's going to pan out. So I think I'm good there. What I'm first going to do is just distribute this. Actually, no, I'm not. I'll leave it. Yes, I will. No, I won't. Shh. I'm going to substitute this into X here and here. I'll distribute on the top one. Equation 1 will be rewritten as 2y plus 2z. Okay, there's the distribution of that. Plus y plus z equals 12. That's 3y plus 3z equals 12, or I can divide by 3 and get y plus z equals 4. There's an equation. In the second equation, equation 2, if I double, see this is 2.5 times 2, well, I can still distribute 2y plus 2z, but I'm going to do 2.5 times those, and those turn into 5. So that cleans itself up. Plus 4y plus 2z equals 160. Let me just box that so I have it. 2.5 times 2 is 5. So 5y plus 5z plus 4y plus 2z equals 160. And now I have 9y plus 7z equals 160, nothing of which can kind of reduce. So I have this equation, we can solve a system with those. Now if I take the top equation right here and multiply, say, by -7, then I can put -7y minus 7z equals -28 and eliminate z to solve for y. So z's eliminate here, I get 2y equals 132, and that'll be y equals 66. That looks way wrong because x plus y plus z equals 12. That looks way wrong. I might have to pause and look back at what I did wrong there. But 160, 2y plus z equals 4. Let me pause and see what I just did there. Okay, as far as work that I showed, I don't think anything was wrong, but I think my setup was now wrong because I'm going back to the bouquet thing, right? What I mentioned before was this was for each bouquet, and I think I'm good with that. The problem is the budget. The budget's $160 for all 5 flowers, but for all 5 bouquets, or 160. Either this needs to be 60 flowers or this needs to be 1/5 the price for each bouquet. So I think this 160 needs to be 32. So I don't know if my answer was wrong there. It's just that I don't think that would work out properly for that thing. So I think that's 32, which means if that's 32, then this here becomes 32 like that. So 32, I haven't solved after that. That's just a fix I wanted to put in place. So 32, 32, 32. Now that seems to actually make more sense for something we can do with it, because 32 minus 28 is 4, and then y would equal 2. So what, two, I forget what these were. Lilies? So 2 lilies seems to make a lot more sense for that kind of answer, right? Okay, because at least it's less than 12. That's kind of where I was getting a little, oh no. Oh my gosh, what happened? All right, y plus z equals 4. So 2 plus z equals 4, or z equals 2. And x is 2 times y plus z. X is 2 times y plus z, which is 8. And so as far as solving that, each bouquet, I think that makes more sense. Each bouquet would have 8 roses, 2 lilies, and 2 irises. Okay, that's the part B, I think. Okay, part C, yes, is in each bouquet. Part C, suppose there's no limitation on the total cost of the bouquets. Does the problem still have exactly one solution? If so, find it. If not, give 3 possible solutions. So I think the idea for that is if there's no limitation, then I don't think the second equation applies. I think you now have an equation here where you just have the top one and the bottom one. I think. So for part C, we're now just looking at x plus y plus z equals 12, and x equals, I'll just say it, 2y plus 2z, like that. So here, when I substitute, now we have a situation where we have, you substitute here, we get 2y plus 2, we saw this, we substituted this before. Z equals 12. We ended up getting what? 3y plus 3z equals 12, and y plus z equals 4. Bottom line for this thing right here is that, this is how those infinite solution set things work. That if y plus z equals 4, you can have any combination of positive. Must you have lilies and irises each time? I don't know. But if y plus z has to equal 4, you can build off that to then kind of do the rest, if that makes sense. Let's see if there's a way on how x needs to be based on that. Does y plus z always have to equal 4? I guess. X is always 2y plus 2z. So let's go based off that. So we have this system here. X equals 2y, well, here, let's do this. Let's get one of these by itself. Y equals negative z plus 4. Let's substitute that in for this x. X equals 2 times negative z plus 4 plus 2z. So x equals, oh, check that out, negative 2z plus 4 plus 2z. So yeah, x would equal 4 in this case. So x always equals 4. Wait, it didn't equal 4 the first time. In this case, x would always equal 4. But that doesn't make any sense. Oh, this is an 8. I'm sorry. X always equals 8 no matter what. Okay, that does make sense. Okay, x equals 8 and y plus z always equals 4. So you'll always have 8 roses. But this one, is there no limitation? Does the problem still have exact one solution? No, you can have multiple solutions. So here are different solutions. You can have 8 roses and then anything that combines the number of lilies and flowers. You can have 1 lily and 3 irises. I keep calling the irises flowers. You have 8 roses, 1 lily, 3 irises, or 8 roses, say, we already did we already do the 2 and 2? Oh, well. Yeah, let's do different ones. 3 lilies and 1 iris. This is irises. Or you can have 8 roses. Let's do 4 lilies and 0 irises. Right? So I guess you can have no irises or whatever if you want to. But that's a set of combinations you can do. There's also a fourth. You can have no lilies and 4 irises like that. But you have to have 8 roses each time, it seems. That's how that thing works in that way. Okay, number 40. How do you see it? Determine whether the system of equations that represents the circles has no solution, one solution, or infinitely many solutions. Explain your reasoning. Well, part A, what you want to have are not concentric circles. You want to have a point of concurrency among all 3 circles. See, these circles may connect here, but the third one doesn't. These 2 circles may intersect one here, but the third one doesn't. These circles may. So it's none of those. So nope, nope, nope. It's about that middle one where all 3 intersect. And they all intersect at one point, which is right there. A has one solution. A has one solution for all 3 circles. It's because they all intersect together. One solution. There is only one point of concurrency for all 3 circles. Concurrency. Is that not spelled right? Whatever. B. No solutions. The circles don't intersect. No solutions. The circles don't intersect anywhere. All right. I like some how do you see it. They tend to be shorter. Number 41, critical thinking. These tend to be longer. Find the values of A, B, and C so the linear system shown has -1, 2, and -3 as its only solution. Explain your reasoning. Okay. It's up here. X plus 2y, minus 3z equals A. Negative x minus y. Wouldn't you just substitute these for x, y, and z? Negative x minus y plus z equals B. And 2x plus 3y minus 2z equals C. We want -1, 2, and -3. Remember, these are your x, y, and z as your single solution. I think you just substitute -1 for x, 2 for y, and -3 for z, and solve for A, B, and C. So A would be x plus 2y minus 3z, which is -1 plus 4, which is 3, plus 9, which is 12. So A is 12. B would be -x minus y plus z. 1 minus 2 is -1, minus 3 is -4. And C would equal, I don't know if I'm doing something wrong, because this doesn't seem like critical thinking. Plus 3y minus 2. I just hope this doesn't have an infinite set of solutions. -2 plus 6 is 4, plus 6 is 10. 12, -4, and 10. You just substitute them. Explain your reasoning. I substituted. I tooted. the sub style. I substituted. Oh, this has been a long video. All right, that's my explanation. Yeah, okay, nice. Normally those are long, but not that time. Number 42, analyzing relationships. Determine which arrangements or arrangements of the integers -5, 2, and 3 produce a solution of the linear system that consists of only integers. Justify your answer. All right, let me just copy and paste that one because it has the blanks there. I feel like it's meant for me to do that. Probably should have done this for other problems, but it's been fine. All right, so 42, we need -5, and we need 2, and we need 3, and we need to figure out which ones get slotted where. Okay, so if I do -5 and 2 and 3, straight up in that order, I'm wondering how there's a fast way to do this. I don't know. How's there a fast way to do this? Because I don't want to do this every time until I get it. That consists of only integer answers. It says determine which ones. I'm more curious in looking at this. The reason I am is because these two are going to be the same this way. So I'm interested in trying one that can eliminate faster and just solve for z. Okay, so I'm going to substitute everything here by, not substitute, I'm going to multiply everything here by -1. And then I'll get -2x plus 5y minus 3z equals +30. When you eliminate those, boom, boom, this becomes -z equals 24. So z is -24. Well, at least that's an integer. Let's take -24 and substitute it into, because that just eliminated both. So now I have to make a system of 2 with these ones. Let's take the first equation and substitute. 6 times -24 is -144. And then x minus 3y equals, add 144, you get 165. 165, it's big. And then in the second equation, we can substitute in here. That's 2x minus 5y plus 3z, so minus 72 equals -30. Add 72 over, you get 2x minus 5y equals, why am I having trouble? 42. So x minus 3y is 165, 2x minus 5y equals 42. Let's multiply this equation by -2 here. So we get -2x plus 6y equals, oh, that's a big number, -330. And then down here we get +2x minus 5y equals 42. At least the x is eliminated and the y's are by itself. We got y equals, and we get -288. Also an integer. So I think x is now bound to be an integer here. So that's going to be now x minus 3 times -288 equals 165. Whew. X plus, what's 3 times 288? It's a 900 minus 36 is 864. 864 equals 165, so x equals, -699. -699, so I have -699 for x, -288 for y, and -24 for z. So -699, -288, and -24. This was if we had the order that was 2, -5, -3. Awesome. So it was my first shot. Now I only did that version because +3. I only used that version of that order just because I saw the x's and y's would cancel. I don't know if that, it said analyze relationships. It says determine which, it says arrangement or arrangements. There might be more than one. It cracked my voice there thinking there are up to 6 possible combinations of this. Listen, I'm not going to do this problem this many times. I'm clocking time like 3 hours in. How much room do I have on my computer for this stuff? Not much. How else should I do these problems that won't make me have integers? That's the thing I don't know. That's an answer. Okay, that's an answer. I feel like if the others aren't, well, here's the thing. I can do it the other ways. It's just 6 possibles. It's just if I keep doing this different ways, I feel like when you solve for one of them and it's not an integer, then it like, then I can stop. And the first time I do it, then I'm good. Still 42 continued. What were the numbers I'm using? 2, oh, they're right here. -5, 2, and 3. So -5 and 2 and 3. Now the order that I just did was 2, -5, and 3. So here are my different options. -5, 2, 3. 2, -5, 2, 3. -5, 3, 2. 2, -5, 3. 2, 3, -5. 3, -5, 2. 3, 2, -5. Now I tried this one and it worked. 2, -5, 3. I tried that one and it worked. Let's try -5, 2, and 3. Is this seriously how I'm supposed to do the problem? Is there something I don't know that I'm missing here? Let's guys, I don't know. Let's put this off to the side. Come on. I don't have much time on my video left here. Let's shrink it. Come on. I'm busy. All right. Let's eliminate x by multiplying. Okay, I'm going to do my own faster version of work here. I'm going to multiply these by 2. How about -2? Actually, it's not much faster, but I might not speak as much here. Let's eliminate here, and you get y minus 10z equals -48. Let's multiply this by 5, and you get -15y. I'm going to do this one kind of fast. -15y plus 2y is -13y. 30, 33, and 105 minus 30 is 75. All right, will this one clean up? Doesn't look like it, but I don't know. Multiply these by 13. 13y minus 130z equals 48 times 13. -48. I haven't used my calculator yet. -48 times 13. -624. -624. So, -97z equals -624 plus 75. -549. And z equals that divided by -97. Not an integer. Okay, scrap that one. So, this one doesn't work. Okay, that was a lot of work just to get there. But yeah, just to solve for a variable. Listen, I could use a graphing well, no, it's 3 variables. So I could use a online one, but there's got to be something I'm not seeing as far as like, all right, this should be easy. But if I never knew how to do them before and analyze whether I get those kind of answers or not, how would I know, right? Same stuff for x though. Let's see. I'll just keep using x with this. Times 5. So -15 plus 3. 30 plus 2. 105 minus 30. What was that, 75? Okay. Times -2. So I'm not going to change that. So 6y minus 5y. Oh, well that won't change, huh? Times -2. -2 is minus 10z equals, and that's -48. All right, let's try this one now. Let's do times 12 on bottom. So 12y, -120z, and 48 times 12. -120z and -48 times 12. -48 times 12. -576. -576. Eliminate those. We now have -88z equals 7 plus 75. Oh, that's not going to work either. All right, so that one doesn't work. All right, let's go to another one. Let's try 2. I'm serious. I don't know if this is mean. 2, 3, negative 5. I don't know if there's supposed to be a pattern of something like that, but I'm just working it out each time. Sorry that I'm erasing the work. I'm not going to keep writing down through this work that I already have. How much more room do I have on my computer? I can probably last 20 minutes max, so let's keep trying to go. Okay, x's can eliminate a lot more easily here. Let's subtract down these lists. Normally I wouldn't, but I'm going to give it a shot. 8y minus 7z, I'll probably make a mistake, equals negative 24. And if I multiply this top one by negative 2, I'll get eliminated, and then 9y, negative 2, negative 12z minus 5, negative 17z equals negative 72. So, ooh, that didn't seem fun. I don't trust this will work. 8 times 9, oh, I don't know, guys. I don't know if that one's going to work. I don't know if it's worth my while giving it a shot. I'm going to probably, you know what I mean? I'm going to probably take my losses. Or cut my losses, if you will, and say that that one doesn't work there. I'm going to say that one probably doesn't work. I don't know. I'm going to hold on. Yeah, I went and typed it into a graphing calculator. It didn't pan out. So okay, so that one's no good as well. So I got 2 more to try. And I'm going to still stick through them with you. It's just when I see something like that, I'm going to do an Uber test if I feel like it's going to be too big otherwise to try it out. So 3x minus 5y plus 2z. So let's try this one. Let's work on eliminating z's this time because both of these could multiply by negative 3 or something. No, let's see. Yeah? No. X is still smaller as far as multiplying numbers. X times negative 2. And I should really write out what that is. But negative 2, 6y minus 5y is y. Negative 6 plus 2 is negative 10. Equals is negative 48. So I have that one. And this one times, or x times negative 3. I don't know if I've seen that one before. 9y minus 5y is 4y. And then negative 18z plus 2z is negative 16z. And then I have negative 20 with negative 63 minus 30 is negative 93. Okay, so with that one, oopsie, multiply this top equation by negative 4. You get negative 4y plus 40. Oh, that's a z. Plus 40z equals positive 192. So that becomes, oh, that's an even plus an odd. So that's not going to work. Does it have to do with just evens and odds? Maybe there's something there. I can't tell, but maybe there's an even and odd connection I could come up with, but it's too late for me to try. Last one to try. Hopefully it works, because otherwise I feel like I wasted my time. I'm lucky to have found it the first time there. Okay. Oh, what was that first equation? Y minus 10y equals negative 48. Okay, that doesn't change no matter what I do for these ones to eliminate x. So y minus 10y equals negative 48. Now this next one I multiply by negative 3. So I got, that cancels 9y, so that's 11y. And then this is negative 18, negative 23. This doesn't look good. And then negative 63 minus 30 was negative 93, right? Negative 93. Okay. Multiply this top one by negative 11. You get negative 11y plus 110z. I keep writing y's here. Those are z's. Equals negative 48 times negative 11. And that's 528. So 528, those cancel, and that's 87z equals 528 minus 93, 435. Oh, that might work. Divide by 87. Yeah, z is 5. Z equals 5. Okay, so far that worked. We'll see if the other ones work. Y should work. Y minus 10z minus 50 equals negative 48, so y equals 2. Ooh. And x will work. X minus 3y plus 6z. X minus 3y plus 6z equals 21. Okay, so x minus 6 plus 30 equals 21. X plus 24 equals 21. X equals negative 3. So this one is negative 3, 2, and 5. Negative 3, 2, and 5 for the numbers 3, 2, negative 5. That's weird. 3, 2, negative 5. So there are two that work. They are these ones right there. Boom and boom. I don't know how to box this really. But these are the ones there with those solution systems. Okay, that was a long problem. Very, very long. And I don't know how to do it without actually doing the problems themselves. Okay, the last question here, number 43, abstract reasoning. Write a linear system to represent the first three pictures below. Use the system to determine how many tangerines are required to balance the apple in the fourth picture. Note the first picture shows that one tangerine and one apple balance one grapefruit. Okay, I wouldn't have known the fruits had I... Okay, so let x... Wait, what's that? Is that... Are those bananas? I guess they're all fruits. So let x equal number of apples, y equal number of... What'd they say? One tangerine and one apple balance one grapefruit. So one tangerine, z equal number of grapefruits. Oh, and they're bananas. Ooh. Write a linear system to represent the first three pictures below. So I have four variables then. So I'll use W for apples. X, Y, and Z is number of bananas, I guess. I don't know. Okay, so we're going to solve for apples in terms of tangerines. We're going to solve for W in terms of X. So we have three different equations. So we have an apple plus a tangerine equals a grapefruit. We have a banana. See, these are the kinds that I hate, right? I talked about this. Oh, let me put this kind of in order. We have a tangerine. I would have just called it an orange and a bigger orange. A tangerine plus a banana equals an apple. And two tangerines, or two grapefruits equals 3 bananas. Okay, here's my system of 3, and then we got to find out how to write apples equals something in terms of x later. So W is x plus z. Let's substitute there. We'll write x plus z plus x equals y. We'll combine those. 2x plus z equals y. We also know that 2y equals 3z. I could rewrite that as, well, I could double this. Check this out. I write 4x plus 2z equals 2y. Now that I know 2y is 3z, I can substitute 3z into here. 3z equals 4x plus 2z. So now 4x is equals z. Z equals 4x. Z equals 4x. So if I have z equals 4x, and I want to rewrite x in terms of w, I can substitute 4x right there. X plus 4x equals w, so w equals 5x. One apple is 5 tangerines. I think that's it. One apple is 5 tangerines. One apple is 5 tangerines. One apple is is the weight of 5 tangerines. All right, I'm not going to really over-explain that one. If you're watching this far into it, then you've probably accomplished what I did with that. I did some substitution, rewrote some things. The one thing you probably didn't notice that I did here was a different kind of substitution. I had 2y here, and I substituted 3z in for 2y because I doubled this part of this equation. That was just something to avoid doing fraction work on that. All right, guys. That'll do it for this one. This is a 3+ hour one. This is Mr. Robinson. Thank you so much for watching. I didn't know what to anticipate on it, and now they figured it out. So, yeah, ask some questions if you have them here, but it was a heck of a lot of work for me. Hopefully a lot less work for you. So, guys, thank you. Take care. I'll see you in the next one.